Good morning. Welcome to day one of the second Alaska Sustainable Energy Conference pre-event workshop for 2024. I'm Brittany Smart, the Energy Transitions Initiative Coordinator at the Alaska Center for Energy and Power, which is the primary sponsor of this workshop series, and I'll be your MC today. Thanks again for joining us. Alaska Governor Mike Dunleavy is very passionate about energy issues for the state and is the primary architect behind the Alaska Sustainable Energy Conference. We are very thankful for his support and leadership in this space. He has generously agreed to make some welcoming comments for us this morning.
Good morning, and thank you for joining us for the second Alaska Sustainable Energy Conference pre-event workshop on the role of transmission and distribution in sustainable energy systems. ACEP was launched in part to start a conversation with Alaskans about our energy future in the context of a global energy landscape. It's not only an opportunity to expand on those kinds of conversations between Alaskans, but to also hear from experts from around the world about lessons learned in other places. I'm proud of ACEP, and my team has put together a fantastic agenda again this year. I hope you'll join us in person on May 21st through May 23rd in Anchorage, Alaska for this year's conference. While ACEP provides a platform for broad thinking and engagement with both Alaska-based and global energy experts, these pre-conference workshops dig deeper into topics relevant to Alaska today. In the last workshop, we heard about energy innovation in the utility industry. Today, we'll focus on the important role of transmission and distribution in Alaska's energy future. In Juneau, the state legislature is considering bills for establishing a rail belt transmission organization. And today you'll hear from Iceland on their approach to establishing a ring grid. What are the pathways and challenges for integrating renewables into our transmission system? We'll hear from two recent research efforts that looked into this and will share their findings. How do we set up a system that can accept power from independent power producers? We'll hear directly from an IPP as well as from the perspective of those who own transmission and distribution assets. Rural Alaska is comprised of numerous microgrids. As we move forward, how are we approaching those opportunities as well? These are all the questions that will arise in today's conversations, and I encourage you to engage with our presenters and panelists. Alaska is fortunate to have a multitude of options before us today. Let's take advantage of the resources we have to chart a path to low-cost, sustainable, and reliable energy for all Alaskans. So I want to thank you for attending and participating today, and I look forward to seeing you in person in May.
All right, as noted, this is the second in a series of 3 virtual workshops. They are being held monthly as 2 half-day Zoom sessions, free of charge, and leading up to the Alaska Sustainable Energy Conference, which is taking place in person from May 20th to 23rd at the Denina Center in Anchorage, Alaska. The purpose of these workshops is to take a deeper dive into specific topics that are of current relevance to the energy opportunity and challenges facing Alaska today. This is the 3rd year that ACEP has hosted these workshops. We bring together some of the top experts and practitioners together to share information and their perspectives on issues that are of interest as we work towards Alaska's energy future. All of the workshops are recorded, and you can find them in the Alaska Sustainable Energy Conference website. Previous topics have included nuclear energy in Alaska, ocean and river energy, hydrogen, low-carbon energy transitions, carbon capture and sequestration, and energy storage. We have posted the link in chat in case you'd like to revisit any of those topics. For this year's workshops, we took a different approach. Rather than focusing on the different technologies, we look at the broader picture of our energy system. Last month, we focused on utility decision-making, navigating constraints, innovating for the future. We heard from utility leadership and independent power producers on their approach to innovation. We learned how they are balancing their current needs with future imperatives while contending with the constraints of governance structures, regulatory frameworks, and legacy technology investments. For this workshop, we are focused on transmission and distribution, the clean energy transition secret weapon. We will hear different perspectives and approaches regarding how our energy transmission and distribution systems are critical aspects of energy infrastructure and are essential for driving sustainable change in Alaska's energy future. We hope you'll join us again next month as we consider betting big, investing in emerging energy technology, where we will be exploring hot topics like hydrogen, grid-forming inverters, and artificial intelligence as promising players in the grid of the future. So let's dive right into it. We're going to go over our agenda slide this morning. We will start by hearing from Gnir Gudmundsson, Director for System Development at Landsnet regarding Iceland's ring grid. Next, we'll dive into railbelt considerations for integrating renewables in a transmission system. This will present findings from two recent reports, ACEP's Alaska Railbelt Electric System Decarbonization Scenarios for 2050, with Steve Colt from ACEP and Isabella Anselmo from Telos Energy. We'll also be joined by Paul Denholm from NREL on their Achieving an 80% Renewable Portfolio in Alaska's Rail Belt, a cost analysis for 2040, and they will be focusing on the transmission aspects of those reports. After that, I will be joined by Mike Kraft from Alaska Environmental Power for a discussion on managing variability and IPP perspective. We will close out day one with a panel discussion on integration from a utility planning and transmission asset owner perspective. I will be joined by representatives from the Alaska Energy Authority and the Matanuska and Chugach Electric Associations. Tomorrow morning, the conversation continues as we learn more about MVDC interties with presentations from Alaska Village Electric Cooperative, Resilient Power Systems, and NANA Regional Corporation. We'll conclude the workshop with current Railbelt hot topics, where we'll learn more about transmission planning and their recently announced GRIP award. Closing us out will be a conversation between Gwen Holdman from ACEP and Andrew Denson from the Office of Governor Mike Dunleavy regarding ideas and actions being considered at the state level. Before we get started, let's take a look at where all of our attendees are joining us from today. To participate in today's polls from your computer, go to pollev.com/TOTTAK216. We recommend using Google Chrome for the best results. The link to the poll is also in the chat. You can also participate by phone by texting TOTTAK216 to the number 22333. You'll receive a text message once you've joined the session. Type and send your response and the results will pop up on the next screen. Can we please see the map? So just to get a sense of where we have some participants coming from, it looks like we've got Fairbanks and Anchorage represented, another one popping in from Anchorage. Oh, we got some down in Southeast. Awesome. Outside of Alaska. All right. That's exciting. Thank you all for taking a moment to do that. For our second question, we're also interested in getting some audience input today. In one word, what do you think is driving our current energy transition? Cost. Yeah, it's a big one. Please just feel free to input your answers right there in the chat function of the poll, and we'll have a word cloud here. All right. Oh, there we go. Now we got some popping in. Cost and climate are still the top ones. We've also got affordability, concerns, opportunity, security, energy security, very important, environmental, reliability. Thank you so much for participating. Oh, we've got some more coming in. We'll give it a moment. Capitalism, capacity, great. Thank you so much for sharing some of your insight. That's really helpful for us. It helps us understand kind of what we think the pressures are coming from. All right, we're going to move to some housekeeping items this morning. Please take a second to introduce yourself in the Zoom webinar chat. Let us know your name and the organization you're from. If you're having any difficulties with audio or trouble viewing the presentations, please send a chat message to Event Support for assistance. During the workshop, all attendees will be muted. Please submit any questions you may have in the chat. Our moderators will collect and curate those questions to be used during the Q&A portion of each section. So for some of these sections, we're going to have a dedicated Q&A for those with presentations. In other aspects, we're going to have facilitated conversations where we'll integrate the questions as they come into the conversation as we're having it. So please, throughout the series, please put those questions in the chat. The recording of this workshop will be available on the ACEP website at alaskasustainableenergy.com at a later date. Please continue to check back for more information, and we're glad to have you here live with us today. Kicking us off this morning, we're going to be starting with a presentation from Iceland. As a reminder, again, please put any questions you may have in the chat, and we'll get to those in the Q&A portion. But for now, please join me in welcoming our first presenter of the workshop, Gnir Gudmundsson, who is the Director for System Development with Landsnet. Gnir, please feel free to introduce yourself and start your presentation. The floor is yours. Thank you so much.
Thank you, Brittany. It's nice to be here with you today. I met some of you in October, I guess, here at Landsnet, and I was interested to meet you again and tell you a little bit about our power system and our challenges. My name is Gnir Gudmundsson, and I have been with Landsnet since 2016. I'm a power system engineer, but I'm also a marine engineer. I started my career in the fishing industry, you know, on a large fishing trawlers, fishing, you know, herring and halibut and other kinds. And then I moved into, and I learned power system engineering and started with the aluminium industry. I was working there for 7 years in, you know, doing investment projects and organizing investment plan and project management. And then I came here to Landsnet, and I have been developing the grid and making the investment plan for Landsnet for the last 8 years. And my team we are 7 in the team, both power system engineers and business analytics. And we are developing the grid with regarding of business. First, a little bit about the Icelandic sector. There are 5 power producers here, and one, Landsvirkjun, has more than 70% of the total energy production. And then there is ON and HS Orka, which have almost the rest. And then there are smaller ones that have only 3% of the total supply. We deliver to 5 DSOs, which have the whole market here, the general market, and they distribute in the towns and in the cities. And then we have 11 high power intensive users, 3 aluminium smelters, it's Century Aluminium, Alcoa, and Rio Tinto, and then 2 silicium producers, 1 power capacitors producers, and then several data centers. And it's the total size of the system it's around 3,000 megawatt hours installed power, but the average peak load is about 2,500 megawatt. If I go over the development of the transmission system, and I will go 60 years back, then we had most of the power was produced by diesel generators. There were several small scale hydro plants, 2 large one in the southwest part, which was connected with 1 single line to the capital city, which is in the south part, and 1 in the north, which was connected to the regional capital of the north, Akureyri. And 20 years later, we had already started this ring connection, and it was actually started from the capital of north, Akureyri, to the west, and it was due to the plans of increasing the size of the hydro plant in the north. But those plants that did not go through due to people living around there, they did not accept that they were changing a salmon river into a power, a dam. So they blew up the dam. So there was no power increase. So a decision was taken to extend the line further to the strong system in the southwest, which was, it was built in 1967 when Aluswiss decided to build an aluminium smelter in the capital area, and the first of the large-scale hydropower was installed in Búrfell in 67. So in 1980 we were halfway through with the ring connection, and 1995 the ring was already there, and we had also finished the ring. It was finished in 1984, and 2019 the system has become much bigger, and over 3,300 kilometers of transmission lines, and several high power intensive users had been added. Yes, all these 3 aluminium smelters. If you look at the grid like it is today, then the total length is over 2,000 miles. I guess you use miles, not kilometers. And we have actually 220 kV grids, one in the south and the southwest, and that is connecting the hydropower cluster in the southern highlands and to the aluminium smelters in the capital area. And then we have another 220 kV system in the northeast part that is also related to our largest hydropower plant here and the aluminium smelter on the east coast. And now we have actually built 2 new lines in the second generation of ring connection. I will come to that later. And then we have this ring connection, what we called first generation of ring connection. It is operated on 132 kV voltage and on 3 poles, wooden poles. And then we have several regional grids. They're mostly operated on 66 kV, but some of them on 132 kV. The security of supply is relatively high, but that is, if you look at, that is measured from energy not served, and that's due to a very strong connections to the high power intensive users, the aluminium smelters. They have usually 2 or 3 connections, strong connections, and they hardly ever get disrupted. But we have considerably less security of supply in some rural areas, like in the west fjords and the west part and the northeast part. The ring connection was established. It took 12 years since we started the first line until we finished the ring, and it changed everything. And by doing that, we were able to phasing out the diesel generator. And that is what we call the first energy transition. The second energy transition is when we start to use the geothermal for house heating, and when we are talking about phasing out transportation fuel, fossil fuel and transportational, then we call it the third energy transition, and that is what we are ongoing today. And by establishing this ring connection, it also increased the security of supply nationwide. So in 1984, since 1984, we have been experiencing a high level of security of supply. But it's 40 to 50 years since we finalized the ring, and the first generation has reached retirement age. We estimate that the lifetime of these wooden pole lines is 50 to max 70 years. And on the smaller picture, you can see the first line, the first line from Akureyri to the west, and it was commissioned 1974, so it's 50 years this year, and our plan is just to take this line down as soon as we have built a new one. There are some challenges in the ring connection. It is the main generation. The generation is mainly in two areas. It's a south and southwest part, and then the east and northern part. And then we have these high impedance connection between, and the security transmission limits is 130 megawatts, and we are in the middle of the Atlantic, and between those two areas is the highlands, and which means that we have different weather systems in the south and the north. When the wind is coming from south, we have a very wet weather in the south coast, and very dry and sunny on the east and northern part. But when the wind is blowing from the north, it's the opposite. Then we have a very wet weather in the north and eastern part, and sunny on the southern. And it is like that it depends on the years if it's more northerly winds or southerly winds that are more over the years. So it's a different inflow into our reservoirs. And this limited transmission limits, we cannot optimize the inflow in the reservoirs due to that. We are only able to transmit these on 130. We often go up to 150 megawatts when the weather is good and there is a little risk of faults. But we lose a lot of energy to these system constraints every year, and it is mainly it describes in excessive overflow of reservoirs, and sometimes it's the reservoirs are on overflow for 2 or 3 months, and estimated cost is $38 million annually, and which is it's a similar amount as we have been using for investing in the system lately. Since we finalized the ring connection in '84, the consumption has increased 5-fold, and you can see the blue area. This is when we were building the ring, and we have 2 very steep, and that is when installation of aluminium smelters, first in '97 and then 2007. But you can see that a normal development is rising, although there are not new aluminium smelters. And the system is sold out. It means that we don't have any headroom. We cannot add any more users to the system, or supply, or production of energy. So it's problematic. And we have already started the construction of 2nd generation of the ring connection. And by that, we are increasing the thermal transmission limits of the lines from 150 megawatt ampere to 550 to 850. It depends on some distances. We are using duplex conductors where needed. So it's 3 to 4 times to 5 times more transmission capacity than we have today. And we are actually doing this, we call it a phase development plan. And the first phase is, our aim is to have that completed before the year 2030. And we have already started that from the east and to Akureyri, and we are where you can see the 2 green lines, and we are planning to finalize that this decade. And that will have positive effect on the headroom nationwide. You can see that we have used this signal lights to express the headroom. Red, it means that the system is sold out. On the northeast part, where we have already installed 2 new lines, then we have already increased the capacity, the headroom, and this is how we see it in 6 or 7 years. And then it's not enough. We cannot stop there. We will have to continue with and finalize the ring connection, and our plan is to refurbish the lines that are south of this last glacier here, and we will, it's planning next decade. We will just refurbish the line and build with higher voltage 220 kV lines. And yes, it is our planned investments for the next 10 years are $1.3 billion US dollars, and it has been, we have been investing for 40 to 50 million US dollars the last years, but it's the same with us as other countries. We are seeing, double investments in the near future, or even triple. But we have to, we are flexible, and we are a little bit concerned of how the development of supply, because our revenues, they are based on our asset base, but the tariffs, if the demand, the demand is there, but the supply is not, not following as we want. So we might be forced to delay some projects if the supply side will not follow soon. But I will come into that later. There are some challenges in the investment projects. Like I said, the composition of the system is unfortunate. And then I'm talking about regarding age. The system it's almost the same age. It's 40 to 50 years old, and there's a growing need for renewal of assets. And there is a government strategy of increasing security of supply in rural areas. So we have several rural areas where regional grids that don't have, a meshed system, so only a radial connection. So we have to, build lines there, and it's not very populated areas, and so it's not a very good business case, but it's a strategy, so we have to do that. And at the same time, the energy transition calls for a doubling of the energy system. We can see that if you want to phase out the fossil fuel, then we have to add 15 to 20 terawatt hours to the supply, and that calls for reinforcement in the system, in the grid. And we are also, experience a very high cost increase in the projects. Everything we have seen that, for example, transformers, the price of transformers has increased maybe to 60 to 80% for the last 3 to 4 years. So that's a huge challenge, and that is, what we have to do is the importance of proper prioritization it's our main focus now, and we are trying to prioritize projects that focusing on return on investments. Yes, and also the supply chain has been getting longer. Lead time for transformer is up to 36 months, and similar with cables. And as I said, the development of energy supply is causing us a little concern now. This is how we prioritize projects. We have, we divide the projects in two main categories. It's the renewable projects and development, and the renewal, it's pretty much straightforward. We are trying to implement something that will extend the lifetime of our assets, and we do that as much as possible. But it's a little difficult with old wooden pole lines that when the wood is just rotten, so that is creating problems. And then we have the development projects. It's either specific connection to power intensive uses, and that is not only aluminium smelters. It's a lot of salmon farms, onshore salmon farms. They are building a lot of those now. They use up to 40 megawatts of power to pump water, and data centers. And then the development of connections to the TSOs, that's based on the government strategy of increased meshing of the system. And then the development of the main grid, it's the second generation of the ring connection, which is in process now. This is our project creation process. We have this energy demand and generation forecast, or energy scenarios, like we call it, future energy scenarios, where we try to predict the demand based on the energy transition and other demand, and then we look at the supply. What power plants are in the pipelines, and try to forecast this. And then we have this 10 years network development plan, which also include 3 years implementation plan, and that is to be confirmed by the energy authorities. And we have recently got one confirmed last February, so we have a good solid plan for the next 10 years. And then we have this project plan approved by our board, and then we will go financing the project. And we have now been working with the Nordic Investment Bank and for some financing, and that is going pretty good. Here's a little bit about our project life cycle. Those lines are overhead lines, and it has been a little bit problematic to get all the licensing for the construction. And this is the first line in the second generation, and only the preparation and the approval process took us up to 7 years. And it was not very problematic. It went relatively smoothly, and it was not work done by us. It was mainly the National Planning Agency and the municipal and others that were delaying the project. And it is possible to, if everything goes like planned, it should be only 4 years, but it's not, unfortunately, not like that. And then there is challenges in the supply chains, and we have been experienced up to 36 months lead time, but we can solve that by doing the project preparation in parallel with the licensing process. So that should not create too much problem. And the construction time, we still have contractors from East Europe, and that is still manageable, and we have been able to get all the contractors we have needed, which is positive. If you look at the future, then we are seeing that a revolution in the electricity market is ahead of us, and then we have this master plan for new power production, and which also contains hydropower and geothermal power, and that is not sufficient to. The lines, they are showing the demand, different scenarios for full energy transition and we are looking at the red line, which is the aim of the government to phase out fossil fuels 2050. So So we can see that, and the columns that is the supply. Where blue is the current, the last year's supply, and the green and the red ones are the power plants that are in preparation phase. And we have problem for the next 5 years. The supply is not meeting the demand, so there is an energy shortage, and lot of users now are curtailed, and we are burning fossil fuel in the fish meal factories and the central heating stations in cold areas. So the energy transition, they're going a little backwards now. But if you look at until 2040, we don't have any more options in the hydro or geothermal. So we have to look at some variable energy sources to be able to carry out the energy transition. And you can see that now this is actually power, but it's similar for the energy. Our energy consumption current is about 20 terawatt hours annually, but we will estimate that in 2050 it will be up to 42.4 terawatt hours. So it's doubling what it is now. Flexibility is key of this. We have to integrate wind energy into our system, and the first wind farm, which is it's a computer picture of our first wind farm, it's in a preparation phase, and we will be connected to the grid, and we are, it is in tender process, the wind turbines, and we don't have fuel plants for generation of balancing power. We have a 100% sustainable energy sources, which it's good, but it creates problem when there is a low flow of water into the reservoirs. So it's problematic. We are not going to interconnect with a submarine cable to Europe. It has been in a debate about that for a long time, but it's not on the government's agenda. So we will not reach that. So increased flexibility is a key objective in our system, and we can do that by increase the power of the hydro plants. Hydropower and wind power, it's good together. So there are possibilities to add turbines to the existing power plants. And then we are also looking at flexible demand, like electrolysis of hydrogen and power to X. And there are a lot of projects in the world that are experimenting with flexible electrolysis. So we are watching how that will go and participating in that. And then we are looking at energy storages like batteries, maybe pump-up storages. There should be some possibilities here, and hydrogen or anything that pops in. But what we are maybe missing, and what's the biggest problem here, that we don't have an active and transparent trading platform for energy here yet, but it's a basic prerequisite for the introduction of variable energy sources. We will start with wind, but we can also see that the solar power will be here in the future. So we are actually preparing to the wholesale market and aiming for a good market. It's here a little overview. Options is master plan. They're not sufficient to meet this, and we have to. There's a huge demand following by the energy transition, and there is a government strategy to carry out the energy transition before the year 2050. And we have been looking at the economy of wind energy, and that is higher than other energy options that we have here. We have already utilized most of our economical hydropower, so it's less viable options left. So we have to develop the wind energy and the system, and to be able to achieve the energy. And we have also seen that without an active trading platform, we cannot integrate the wind into the system. So that is our biggest goal now with the expansion of the grid. So this is the last slide. So I hope you have had some gain from this. Thank you.
Thank you so much, Gidnir. And there's a lot of similarities between Alaska and Iceland. And in fact, ACEP's done a lot of work looking at those similarities and differences. And I'm going to put a link in the chat here real quick with just some research ACEP has been doing in regards to looking at Iceland's system and potential lessons that we could learn here in Alaska with extreme climates, similar populations, geographical distances. There's a lot of things that we have the opportunity to learn from Iceland. In fact, we hosted a policy tour, which you referenced earlier, and we spent quite a bit of time with you all. So thank you for the time that you spent. We've had some great questions come in, so I'm going to ask you to expand on some points. We got our first one from Amy, and she says, thanks for presenting. Could you take a moment to characterize how much renewable power generation is used on the system and which resources? Is it mostly hydro or are there others?
Yeah, it's all renewable, 20 terawatt hours a year, and 75% is hydro, and the rest is geothermal. We have these large geothermal plants that are mainly used for heating of water, but first we take the electricity from the steam. So 1/4 of our energy, our electricity power is coming from these geothermal plants. So we are so lucky that we have a very active volcanic landscape here, but it's actually erupting now. So we have been having a volcanic eruption every month for the last 4 months since November. So
it's very active. It was just starting to get going when we were visiting. So, and one thing I recall from our visit is, the geothermal does heat the majority of the homes there. And due to the cost of electricity, when a home was getting too warm, the solution wasn't to turn down the heat, it was to open the window. That is not a problem we have here yet in Alaska in terms of the cheap energy. And so that was just an interesting perspective to witness. Our next question is, would large-scale wind generation be able to step in more quickly than new hydro in order to provide more power?
Yeah, up to some point. Maybe we can add 200, 300, 400 megawatts installed wind power to the system. But after that, we have to integrate some means of flexibility in the system, because we don't have enough regulating power to compensate for the wind. But it's definitely what we are doing now. We are building a wind farm, the first wind farm because we need the power we need it fast. So that's the next power plant that will be commissioned in 2026, I think.
Later on this morning, we're going to have a conversation with an independent power producer of a wind farm. And one of our conversation points is how to deal with variability. So we know that with some of these power sources, they come in different times, and how we manage that with the system. Is that something that's of concern, or how are you approaching and managing variability with this new wind project that you have?
That is our, that's our main challenge now. So my division, my team, we are investigating the best way to do it, and we don't have the solution yet, but we are developing. So, but that is absolutely our biggest challenge in the coming years. So if you get any good ideas, please let us know.
Absolutely, we're happy to share any.
Yeah.
Another question, have you evaluated high voltage direct current HVDC transmission options between your two major service regions? Also, can you describe the role of any government subsidies in the project?
Yes, we have that. We are considering a connection over the highlands, the straight line between the two generating clusters in the northeast part and the south part. And the highland it's a strategy that we may not build new overhead lines over there, and we have not the short circuit power to add, to have underground cables, AC cables. So we have looked into DC connection over there. It's 230 kilometers, but it's very expensive. It costs almost the same as half of the ring. So, and the government has not yet approved to participate in the cost. So, but we have looked into it.
What is the main cost driver for that?
Yeah, it's the transformer station. It's the what do you call it? The inverter stations. We have to transform from AC to DC and on both ends, and that cost I think it's 70% of the cost, 70 or 80.
Would that shift as you move forward help reduce any rates or increase efficiencies, or
yes,
what impacts
it will impact. It will have a very good influence on the system because with DC we are able to control the flow. We can just control how much will flow through that connection. So by controlling that, we can control the flow on the rest of the system, and it will have a very, very good effect on the remaining of the grid. But so it's a good option, and also it's underground cables. We have to light 2 cables instead of 3, but it's the cost. It's the only thing that is preventing us from doing that. It's the cost.
Understood. Well, we'll look forward to seeing that project develop.
Yeah.
Do you consider that the status of investments in the transmission system is similar in Iceland as in Northern Europe?
Yes. I was actually in Amsterdam 2 weeks ago on an energy transition summit, and we saw some presentations from other TSOs in Europe, and it's the same. They are doubling the investments in the next 4 years. So it's our investments are absolutely similar to others in Europe. I don't know how it's in America, but it's definitely the same as in Europe.
And then we're getting a slew of questions in here, and I know we got a little bit ahead of schedule, so if you don't mind, I'm just going to keep trucking through them here.
No problem.
The next one is, are you considering nuclear or geothermal generation in order to meet demand in the future?
Nuclear? No, we have actually not. We are not. No, I think there is some kind of policy here not to install nuclear power.
Interesting.
So, yeah.
Is that just a adopted policy, or is that just a general public sentiment?
I think it's a general public, but we were actually looking at this energy transition summit in Amsterdam. We were looking at some micro nuclear plants that could benefit us in some rural areas. They are producing 20 megawatts of electric power and 60 megawatts of thermal. But what is needed in some parts of Iceland, cold parts, but there has not been any debate about it.
Interesting.
Not yet, at least.
So the next one gets into, do you have any time of use rates on your grid?
Excuse me, can you?
Do you have any time of use rates? So is there any incentive to use power at different times in order to like lessen peaks?
No, not yet. No, it's the same. It's the same tariffs for the whole country and 24 hours. And we haven't, but we are talking about it, but we have not implemented yet, and that will be more on the DSO levels. The DSOs they have larger problems, dealing with charging of electric vehicles in the neighborhoods. So they are thinking about it more than we.
Yeah, and going back to your presentation, I recall that you said, I think it was 85% of your power demand is from the industry.
Yeah.
And those have, some pretty set rates. And so those are pretty moderated, when those polls are. I also recall seeing quite a bit of uptick in electric vehicles. You just noted those. Are you seeing that could be a challenge if you're already at capacity? Do you foresee a challenge of increased adoption of electric vehicles throughout Iceland?
It's depending on the location. The majority of the vehicles are here in the capital area. And it's definitely a strong need for grid strengthening in this area. But in other parts of the country, it's not. There are not so many vehicles, but we are actually the first generation of the ring connection, the 132 kV grid. We are not, we will keep that in operation, and that will change the role into be a part of the regional grids. And then we are, mainly focusing on charges, charge stations along the highways. So I think we are pretty much covered by that.
All right.
We have already planning to put up new substations on the old 132 kV ring on several locations to cover, fast charges. Because on the main road from Reykjavik to the capital in the north, we are estimating that we need 200 fast charges on that road. So, people are driving there on Friday, on Sundays. There's I don't know how many vehicles are on the way, many thousands, and if they're all electric, then they all need to charge. So that is a little bit challenge, but I think we got that solved.
That's great planning into the future. That's something that we're still grappling with here in Alaska, is how do we make sure that we have the infrastructure we need as those consumer expectations change into the future. We had a question regarding the third energy transition. I'm going to preface this again, going back to that visit that we had in Iceland. We heard quite a bit about the public expectations of moving to a zero carbon future, especially in regards to expanding energy transitions into port and air travel. I don't think this will necessarily get all the way to that point, but the question is, how will the grid be adapted due to the third energy transition to ensure that the higher demand can be matched and to improve energy security? Can you speak to kind of both of the public sentiment as well as your approach to meeting those expectations?
The biggest part of the energy transition is the aviation, and the ships and the aviation, and it's important that it's also part of the flexibility. It's the location of the if we want to, we can choose if we want to import the e-fuel, or we want to produce it ourselves. Our strategy is to produce it here, and then the location of the Power-to-X factories is very strategical. It has to be close to, large wind farms or something. But but we don't know. But we are trying to control the discussion that way, that we can have some influence on where these factories will be located. I'm not sure if it answered the question, but
I think it was about as best as I could have tossed your way.
okay.
We do have a question regarding, can you speak to the potential or what you've observed in terms of environmental impacts of hydropower? Are you seeing any? And if so, how are those being managed from your perspective and into the transmission system?
It is always more and more difficult to get permission for hydropowers. People, they are starting to fight against it a lot. So I think there is not so many options left. We are there are one hydropower plant in preparation now, which is in the south area, and the same river as it's a plant number 7 in the same river. But people are fighting against it very hard. So it gets more difficult every year. So I'm not sure that we will see so many new hydropower plants in the future. Maybe 2 or 3.
So we do have a comment here from someone saying, thank you so much for presenting. What a cool network. And I'm going to build on the river, which is why I'm jumping to this one. I would love to know how river ecosystems are preserved when hydro systems are installed and running. And I think that gets to your point where the public may be getting more and more concerned with some of the hydropower systems that you have, and you might start seeing fewer and fewer of them. Can you speak to a little bit about how those ecosystems are being preserved? Is that something that you work on at all from the Landsat perspective?
I didn't get what can you repeat?
Yeah. How are the river ecosystems preserved when hydro systems are installed and running?
Yes, it's a tough one. Like the one which is in preparation now. It's in one of the largest rivers, and there is a salmon, stem there, which is the largest one in Europe, northern Europe, and they have been making some models of something to let the salmon by, but people are very skeptical about it. So that is the main reason for that. That particular power plant has been 19 years in preparation. That is due to this wild salmon, which is there, and it is increasingly people are concerned about the wild salmon. I guess you have a wild salmon in Alaska too, and also the offshore salmon farms, they are also threatening the life of the salmon, wild salmon. So all this together is something that is working against further hydro power, especially in those rivers that have these salmons. So
yeah, that's something that we struggle with as well. So we've got some projects here at ACEP that are looking at that, and timing and understanding the river flows and the salmon runs. So definitely a lot of lessons to learn and continue to learn.
I'm not the right person. I'm not in this environmental. There are other divisions, but that's only what I read in the news. So I'm sorry about that.
No, thank you. So going back to wind, we have a comment. Very interesting, the idea that an active trading platform is needed to integrate wind. How did you come to this conclusion? And did you try to model the integration as just an engineering problem?
Yes, it's of course it's an engineering problem, but I think the biggest problem here is we have too few producers which are producing too much part of the energy, and they're not willing to participate, in this free market. They're just, they have these long-term contracts with a high power intensive users, and I think it's going to be difficult for new players to build wind farms, because there is such a small ratio of the energy which is on the market. So it's difficult to get regulating power because we have too few players on the market. So we are aiming for this wholesale, I don't know how to express it, but like now, because of this market situation, the price is very fixed. They control the price, and we haven't had any price signals for many years. So that's why new players have not built a new power plants, even though there was a lack of energy, but the price is too low, so that we have not been able to, new power plants, they will not pay off, and this is according to our analysis mainly due to too few players on the market that they control the price. So there are no healthy price signals in the market.
So the statement has been made a couple times how you don't have much more capacity to provide energy at the moment. And during our tour, that was a very interesting conundrum, almost a problem that Alaska would love to have. As we've stated, 85% or so of your energy demand is coming from industry, and you still have industry interested in knocking at your door, wanting to operate in Iceland. And Iceland is in a position to really start questioning whether they say yes to some of these industries entering the market. And it has to do with the cheap cost of power in Iceland. So as we talk about some of these things, I think that's a very interesting perspective to keep in mind here as we move forward. Again, I know that's something Senator Bishop in particular during the visit was just really interested in pursuing the questions along those lines. Again, keeping on wind and hydro, do you expect to operate your storage hydro projects any differently in order to integrate wind into the system?
I don't know yet. So it's something that we are very short in the way of processing it, and so I'm not sure how that will work out yet.
Okay. In Iceland, what are the main drivers for increased demand of electricity? I think we were just speaking a little bit to that.
Yeah, it's both the energy transition and also there is, like you said, there is a high demand for power intensive users, and it's mostly the data centers and these onshore salmon farms, for example. There are environmental the environmental people, they are fighting against the offshore sea salmon farms, and they are bringing it up to land, and that is very power intensive. So there is a high demand, and we estimate that the growth will also come from there. And we have been, we are talking to the municipalities in all over the country, and we can feel that people, they want to have better connections, and they want to have access to energy to build up their industries for the people. So there is it's not only energy transition, it's also industry and small scale industry, greenhouses, large scale greenhouses, and lot of things. So I think it's about 30% of our demand is coming from something else than energy transition.
Yeah, Iceland's also been doing incredible things in using energy to support local food production. I was actually blown away by the amount of food that's actually produced and consumed in Iceland, and it's all delicious, of course. We have got just a few more questions here. We might not be able to get to all of them since we're now running up on time. What would be the one single most profitable investment for the ring grid?
Definitely to finalize the connection, the first phase, to finalize the connection from the southwest to the east. And we need 3 more lines because then we can avoid the spillage of the reservoir, and that will save us about up to $40 million every year.
Wow.
And I think we estimate it's about around 300 to 400 gigawatt hours in average that we lose from the system.
Okay, I think I got about 2 more here. Do you expect geothermal to be available indefinitely or only for a limited amount of time?
We are still very active, volcanic activity is very high here. So we will, of course, we have to drill some new holes and maybe move the locations, but it will be here in definitely maybe at least 100 years or more. Absolutely.
Sorry, I miscounted. It looks like 4 more. Thank you. I'm going to just go through these last couple so we can finish them off. Yeah. Are there any incentives to increase consumers' energy efficiency to temporarily overcome the supply shortage?
No. The energy price is too low, so there is no incentives. People don't care. There are no price signals at all, so there is nothing.
Yeah, I guess to further reiterate how cheap the energy is, again, Senator Bishop was asking individuals that he met in Iceland what their bills were, and it was so cheap that they would just say, I don't know, because they don't pay attention to the number. It was just that cheap. So again, I linked the ACEP research. Some of that is covered in there, and that's definitely a space that we've been looking into and how some of those lessons learned can be applied to Alaska. How is the acceptance of wind farms compared to the acceptance of hydropower?
It depends. It is if the wind developers have gone the right way to the communities and do it together with the communities, then the acceptance is higher. But the regulation is actually, the regulating work is not in place. The parliament is setting they have been building a strategy that has not yet been published, but we are hoping that we will get some good frame of where to locate the wind farms and get a good support from the public support for it. But it's easier than the hydro, definitely. Most places.
And then our final question right now, do you think Iceland will be energy deprived in the future?
Energy
deprived. What
does it mean?
It means that you won't have any energy. You'll have used it all.
I don't know. We have, of course, we have these large users which we can, the contracts, they are not going to last forever. And if that situation will come up, I think the contracts will not be renewed.
Yeah, so to expand on that, a large driver of Iceland's energy transition was the aluminum smelters that came in, which required a high level of energy in order to do their process, but they were coming in from outside the country and they have these existing contracts. So as the demands locally increase and as public perception and sentiment around some of the potential impacts of these industries become more concerned, there are opportunities for Iceland to consider what those contracts look like in the future. So again, with industry being a huge driver in the use and cost, bluntly, of Iceland's power system, there are opportunities to mitigate some of those moving forward.
Absolutely. I can also tell you that recently in the newspapers, one of the power producers, ON, it advertised 150 megawatt of powers available in 2 or 3 years. That is a contract that is expiring from one of the aluminium smelters. So they're just putting it in the market just to probably, I don't know why, either to as a part of negotiation about a new price, or they're just investigating the market. So things will change, definitely.
Yeah. Well, thank you so much. That was quite a series of questions that we had from the audience. I really appreciate the engagement. And Gnir, thank you for joining us this evening or this morning for us. We appreciate you taking your time away from your family to share some of the lessons from Iceland and sharing about your transition to the ring grid. So again, thank you so much for your time today.
Thank you. It was a pleasure.
All right.
Okay.
All right, that was quite the presentation to kick us off this morning. So thank you once again. Next, we're going to be looking at some recent research reports that have been released, and we're focusing on the transmission system of those two reports and looking at some of the similarities and maybe some of the differences between the two report findings. So what we're going to do is we're going to start off with Steve Colt from ACEP and Isabella Anselmo with Telos Energy, and that will be followed by Paul Denholm with NREL. We're going to do the two presentations and then we'll do a combined Q&A at the end. So please continue putting those questions in the chat and we'll get to them. And with that, Steve and Isabella, if you would please take a moment to introduce yourselves briefly and tell us about your role within your companies, and then take it off with the presentation. Thank you. Go ahead, Steve. You're muted. There you go.
Thanks, Brittany. I think I'll let Isabella introduce herself when we get to her part of the slideshow, and she may do her own sharing, but I'm going to start by trying to share my screen and find the right thing to share and ask you how it looks. Looking good?
Looks good. Yep.
All right, I'm going to give a very brief contextual introduction to Isabella, who's really got some interesting stuff that's pertinent to today's topic of transmission networks. The ACEP decarb study looked at 1 year, 2050. Got to get my screen to advance. There we go. We looked at the rail belt electric grid. We have published one main report, and we have recently completed we're about to complete one addendum to that report. Those are the two main work products that you might want to look at more carefully. It's important for us to recognize, thank, and appreciate the fact that this was a very collaborative effort. We had tremendous help from the Rail Belt Utilities, the Alaska Energy Authority, and other individuals associated with them. We had help from our collaborators in Hawaii. We had financial help from federal and state support, and could not have done it without all of this collaboration and help. The project was conducted in multiple stages. Unfortunately, all the arrows tend to go in one direction. We were not able to iterate backward between some stages and others, which would be best practice if we had the time and resources. But nonetheless, we tried to capture the main elements of a comprehensive analysis. And we ended up for the main report with 3 low carbon scenarios, each of which had what we could call an anchor tenant or dispatchable, reasonably dispatchable supply. One was a big hydro project, one was a big tidal project, one was 2 or more medium nuclear projects. At any rate, the low carbon scenarios were all anchored with some kind of anchor tenant dispatchable resource in the main report. Another thing to keep in mind is that we, like Iceland, are essentially looking at a potential doubling of the load by 2050 due to EVs and heat pumps. And so we were aiming to meet that doubled load. I'm almost done. Just two or three more slides about how we got to where Isabella will take over. We looked at resources, particularly the wind and solar resource, and we ran a sort of highly simplified capacity expansion algorithm, if you will, trying to look at what kind of sizes would make economic sense particularly for wind and solar. And as I said, we had anchor tenant projects, and those were essentially predetermined as to size. For example, we used the Susitna-Watana hydro project as one of the anchor tenant supply side resources. And the last thing we did before we get to Isabella's work or the last thing I need to just tee up here is that we took the resource analysis, the sizing of wind and solar and other components. We put those through a dispatch model, production cost simulation model, if you will, and that the key thing that does is try to ensure that the supply is sufficient to meet the load in every hour of the year. And then that leads us to the transmission analysis. And I'm now going to hand this off to Isabella, but with one last contextual piece of news. If you've been following our study, you may notice that this wind solar bar is new. This is a new scenario that we have recently been able to run. And what it does is basically build more wind. And in terms of annual energy, it's interesting to me anyway that it is only able to achieve about, 77% carbon reduction on an energy basis, not as much as our hydro scenario or our nuclear-based scenario. So that's a quick introduction to the transmission analysis that Isabella from Telos Energy is going to discuss. Isabella, you can share your own screen, or I guess you could keep using mine if you want to say next slide. It's up to you.
Okay, we can use our slide. I think that's good. Hello, everybody. I am Isabella Selmo. I work with Telos Energy. I'm a power systems engineer. And we partner with ACEP for this renewable decarbonization project that Steve introduced for us. And I'm going to focus on the transmission analysis, especially of the wind and solar scenario, which is the addendum. If you want to check the original report, it is available. The addendum, it's still not published, but we hope to do it soon. So next slide, please. So we already saw this slide, but it's just a context to compare how this new scenario is compared to the others. We have more wind, solar, and storage on this new scenario, which means we have more inverter-based resources in our system. And this is where the transmission analysis gets interesting, because with more IBRs in our system, we have more challenges to address in the stability point of view. So next slide, please. So what is this scenario differs from the others? So in the grid operations point of view, we have the challenging hours which we use to address the stability have changed, because we have more IBRs online, so we have more challenging hours, and these hours shifted a bit. And also the flows on our interties have changed, especially when you talk about the Kina intertie in the south flow direction. I will give more details on this on the next slides. Something that we did different on this scenario compared to the others is that we analyzed an additional contingency, which was nice because this was particularly severe when we have flow direction now south from north to south, and we are going to talk about that too. And we also analyze different mitigation options. So before we were focused on planning more transmission upgrades and resources, but here we also compare how some operation mitigations can be used in a smart way to prevent increase the costs of all these upgrades that we're going to do. So next slide, please. So this new scenario, what is different and why is so challenging? So we see here on the graph that these are the hours of the year for a generation on the 2050 scenario. This new scenario, we have much more hours where we operate with IBRs, and we actually have thousands of hours where the rail belt just operate with 100% of inverters. And why is this challenge? Because historically, synchronous machines, which are the generators for conventional generation, they are critical for the stability because they provide inertia to the system. Once we retire these machines, we have less inertia in the system, and it means a weaker system. So in a context with a lot of inverters, we have a weaker system and it complicates our stability. However, we have new technologies that are emerging, like grid-former inverters, that helps a lot in the stability context. But we can also apply some conventional machinery like synchronous condensers to keep the stability on their system. Next slide, please. Another challenge that we face on this new scenario, it's regarding the intertie flow, especially on the Kina intertie in the south. So if you can see here on this graph, for the most part of the year in all of the scenarios, the Homer area in the south is exporting power. So naturally, the flow on the Kina intertie is south to central. There are some few hours of the year for all scenarios that this flow is reversed, but for this scenario in particular, this reverse flow has increased. And this is where we saw some new violations and different contingency causing problems in the system. So it was a new thing to analyze here. So next slide, please. So to conduct this new scenario, we actually used things that we learned from the other scenarios, especially regarding the grid-forming inverter batteries. So here's an example. We have the hydro scenario. We initially, when we were dealing with the stability on the system, we are using batteries for stability support. But when we model as the conventional grid-following inverters, we had a system collapse. So they were not able to support the system. We are able to address the stability problem with some synchronous condensers, but we got the best performance when we model our batteries for support as GFM batteries. And we were able to achieve stability on the most critical cases on the other scenarios. Because of that, we applied the same approach here on the wind and solar scenario, which had much more challenging hours. Next slide, please. One thing that we learned from the other scenarios was that the places that we place the location where we places those batteries for support, they are critical. We identify them by doing all the transmission analysis. So on a typical transmission analysis, we start doing by doing the steady state analysis, where we identify thermal violations and voltage violations. And with that, we can propose some transmission upgrades and some equipment for voltage support, for example. After that, we can go for the dynamic analysis. And it's on the dynamic analysis where we see the problem of inertia and the retirement of synchronous condensers that synchronous machines cause. So we identified the critical buses that we needed to place, the support batteries, doing the dynamic analysis on the other scenarios. With the batteries placed on these specific buses, we are able to achieve a reliable system. And also, this helped us to have an approximate idea of the sizes of the battery that we need. Because although this new scenario has different generations, the sizes of the loads are similar. So we needed similar support, even if the challenging hours are different. So next slide, please. So here we have the simulations of the loss of both interties, Alaska on the left and Kenai on the right. And we see that the system got kept stable during this contingencies because of the batteries, the GFM batteries that we place on that key points with the similar sizes of the previous scenario. So it was interesting that even if this scenario is more challenging, the point of view that we have more hours that we need support, the sizes of the batteries that we propose for the other scenario, they still stand true here as a point of view of stability. They were effective in keeping the system stable when we had those contingencies. And placing it in the correct points help us to reduce the size of these batteries. So next slide, please. Here we have the additional contingency, which was the loss of a 230 kV line in the central area that we analyzed for this scenario and not for the others. And what I want to point here on the left is that for most hours of the year, we didn't have an issue with this contingency. The system kept stable. However, when we have this particularly flow on the rail belt, things can get weird. We have a problem. This happened specifically when we have the flow on both interties going from north to south. So the flow on the entire rail belt is going from north to south. If we lose this 230 kV line, all the power that was flowing through this line is forced to a path that is kind of weak, and it makes the rail belt loses its synchronism. And we just saw that when Homer was importing a lot of power. So when the flow on the Kenai intertie was reversed, central to south, and it was high. And this happens in a few hours of the year. So we decided to check different approaches. So we were able to address this problem with a big GFM battery on the central area. So we are able to mitigate all of this loss of synchronous and these oscillations you see here with a battery. Another option would be transmission upgrades to provide a new path for power, so the power would not be forced into that weak connection between north, central, and south. And also, there is another option for that, because as I mentioned, the flow central to south in the Kenai intertie just happens in a very few hours of the year. So we can restrict the flow on this intertie and be able to mitigate the problem if we lose that line. Next slide, please. So because for this contingency, we saw that we could have different options, we decided to check different options for other major problems we saw during our analysis as well, something that we didn't do for the other scenarios. Here are some examples. So for example, there is a lot of thermal overloads in the north on the 60 kV system in the north when we lose a particularly on 38 kV line on the area. And we can solve that with a new big transmission project. However, we saw that this was only true, these thermal violations was only true when we didn't have local generation on that area and the load was very high. So we didn't have local generation to feed that high load. So another option to solve this issue would be to provide that local generation. So if we dispatch, for example, North Pole fossil plant for more hours during the winter where we have high load, those thermal violations, they are gone. So we wouldn't need to build this huge transmission project. We would just need to dispatch this plant for more hours. The same thing happens on the central area. That same loss of line that we saw on the previous slide also causes thermal and voltage violation on the 115 kV system on central area when we don't have local generation. One thing that we can do to solve is a big transmission project. There is this Lorraine substation that was proposed in one study in the past that interconnects with other substations on the area. So this substation and its interconnections prevent the thermal and voltage violations in the case of this event. But we can also mitigate this problem if we have local generation on the 115 kV system. One example would be to dispatch more hours the George Sullivan fossil plant when we have peak load during winter. However, we saw that the loss of this line also causes the dynamic instability on the system, and the generation redispatch won't do the trick here. But as a weak equipment mitigation, we can put a big battery on the area and it solves. And also that Lorraine substation that we talked before also helps on that. So here we have two options. But as we saw, the problem with synchronism just happens on the few hours of the year when we have a high flow going central to south. And this happens like roughly 100 hours of the year from our data. So if we restrict the flow on this direction on the Kenai intertie, we would be able to solve the issue of this loss of synchronism. Next slide, please. Here is a summary because we focus all the stability on the GFM batteries, and the GFM batteries, they're actually nice for the stability because they not only provide a fast response and are able to help with the inertia issue that we mentioned, but it also has really good quality when we are talking about voltage support because it's a fast support and it has the capability to give continuous reactive power. And also, in the case of a contingency, it is able to sustain the response for a good amount of time. Here we have a comparison for all scenarios. I just want to point that the wind and solar 300 MVA from this is for that specific contingency that we talked about. So if we are comparing apples to apples, we would say that the wind and solar would need 925 MVA, which is between what hydro and nuclear needed when we analyze. So these results are actually really nice because we saw this scenario has a lot of renewable energy, a lot of IBRs, and we didn't needed much more equipment for stability as we needed on the other scenarios. So we can enable this scenario with the roughly same amount of equipment. I think I just have one slide left, maybe. Yeah, just as a summary, this scenario was very challenging because we have much more hours where the only IBRs are online, and we had some shifts on the intertie flows, and they were increased. But what we learned, which was really nice, is that the same mitigations that we proposed for the other scenarios were still true here. And especially the GFM batteries combined with the best technology for wind and solar plants. But I think one of the nicest outcomes of this part is were the mitigation options, where we saw that we can do smart decisions to prevent the cost to rise a lot. So we can combine some of the transmission upgrades that we see that would be more necessary, but we can also apply some operational smart decisions to have the best cost-effective scenario of all. And I think that's all I have. Yes.
All right, thank you so much, Steve and Isabella. As I mentioned, we're next going to go to Paul Denholm, and he is going to be presenting on achieving an 80% renewable portfolio in Alaska's rail belt. Paul, thank you so much for joining us. And again, audience, we are going to do a combined Q&A at the end, so please put your questions in the chat. Paul, thank you so much for agreeing to participate and present today. Please take a moment to introduce yourself real quick, and the floor is yours. Thank you.
Great, thank you. Again, my name is Paul Denholm. I work at the National Renewable Energy Lab, where I'm a senior research fellow focusing on grid integration of renewables. So I've been working on grid integration of renewables for about 20 years, studying various aspects of how much wind and solar can you put on various grids around the U.S. And happy to get a chance to work in Alaska as well, representing myself as well as Marty and Lauren, who worked on this project. So yeah, the focus of this particular study was really on the cost of implementing renewables, kind of understanding what are the cost challenges, what are the potential benefits of integrating renewables onto the grid to replace potentially increased costs of liquefied natural gas imports. And I'll focus a little bit on the overall results, but also the role of transmission and the importance of transmission in integrating renewables into the grid, because again, the transmission is really important. So fortunately, the ACEP study kind of went over a lot of this, so I don't have to go into a whole lot of detail about the rail belt. But one note, kind of in context, the potential importance of addressing the cost issues is the relatively high cost of electricity in Alaska. The average residential rate in Alaska in 2022, about 23 cents per kilowatt hour, or sorry, the average rail belt rate in 2022 was about 23 cents per kilowatt hour compared to the national average of about 14 cents per kilowatt hour. So there's already a substantial increase in electricity prices in the rail belt compared to the rest of the lower 48. And this is expected to rise with projections of the need to import liquefied natural gas. So these are the cost projections that we used based on some numbers that we derived from various sources in Alaska, talking about how potentially price of natural gas going up to something like $12+ per million BTU. This would raise rail belt electricity costs by about $75 million per year, if kind of under a business as usual scenario. And given the fact that about 2/3 of the electricity generation in the rail belt comes from natural gas, this kind of presents an exposure issue of price volatility and risk with maintaining such a heavy reliance on natural gas. And so, again, the question is, what might the cost impacts be of replacing some of that gas-fired generation? And one important thing to talk about is when I talk about renewables replacing natural gas generation, I'm not talking about renewables replacing the physical capacity. I'm talking about them replacing the energy. So basically, renewables acting as a fuel saver for the existing natural gas plants. You're keeping them around, you're just using them less. And so that's what we're looking at. And so the idea of this study was to say, okay, what are the differences in costs between various cases? And one really important thing is we're only looking at the differences. We're not looking at kind of the cost of maintaining the existing fossil fleet. I mean, you're going to need to do that regardless of whatever scenario we ran here. So the existing debt, the cost of maintaining the existing transmission network and the existing distribution network and sending out bills and everything, that's not what we're talking about. We're talking about, okay, if I have to build a new plant, how much more will that cost? If I displace some fuel, how much less will that cost? So we're looking at the difference in costs across the scenarios, including a large number of costs associated with integrating renewables. That's always a big question, is how much does it actually cost when you start talking about the increased variability and uncertainty? How much natural gas storage might you need? How much additional operating reserves, things like that. So we wanted to compare across all of those different cost categories across these different scenarios. To do that, we kind of follow the standard, what's often called integrated resource planning approach. You use a capacity expansion model to do an optimized mix of resources, what's the least cost mix of resources that maintains reliability, and then doing these hour-by-hour simulations of how would you actually operate the grid using the Plexus tool, the same tool that ACEP used. So there's a lot of similarity between the two studies in the approach. The biggest difference would be, our focus is really on the costs, and focus on what the optimum mix, as opposed to doing the dynamic stability analysis, which we did not do. So we did kind of three basic scenarios. The first thing we did was a no new renewable scenario to understand what's the cost implications of continuing to burn natural gas at its increasing cost. Then we did what we're calling a reference scenario, which is what is the model's choice for the least cost mix. No restrictions on what it can build. It can build new gas, new coal, it can build new renewables, placing no restrictions on what it can do. It could just do whatever it's doing right now. Or let it build new renewables. So that's the kind of the least cost mix. And then we also did the RPS mix, which is enforcing the 80% by 2040 RPS standard. And the eligible technologies for the RPS include a variety of technologies, some of which we did not consider. So we didn't do, for instance, tidal, and we didn't do new large hydropower. We didn't have good cost data on what that might cost. So that's one of the definitely bigger deficiencies of the study, is the lack of consideration of large new hydro, including things like the Dixon Dam diversion. But that's the core three cases. And then we did some reference cases where we increased renewable energy costs by either increase them by 20% or decrease them by 10%. So in terms of the transmission framework, it's pretty straightforward in terms of what we did and didn't do. We did a 3-zone model, kind of similar to what you saw earlier. There's the kind of the GVEA zone, the central zone, which is Chugach and MEA, and then the southern or HEA, Homer Electric zone. There's no transmission constraints modeled within each zone, but the big thing is, what can you push along the Alaska and Kenai interties? We did not consider any upgrades to the Alaska intertie. It's 78 megawatts of transfer capacity, either north or south, and we did not consider any ability to potentially upgrade that. But the Kenai intertie, we assumed that as part of the Railbelt Innovative Resiliency Project, so there's some money, some federal dollars that are coming in to help upgrade that system. We considered an upgrade along the entire path, either kind of in the combination of the existing plus new, of 185 megawatts. We did not assume that the transmission could be used for the purposes of maintain reliability. You have to make sure that you're within your zone, because these transmission lines go down. So you have to make sure that you're reliable in each zone. We also didn't allow for sharing of operating reserves on these transmission lines. So these lines are primarily for an energy exchange purpose only, to minimize cost. And for that purpose, we did assume that the system is optimized in terms of how it's operated and planned, in terms of something like a joint dispatch, or kind of some way to better optimize the system, so that you can always exchange power from one region to another without incurring additional kind of transmission costs, kind of wheeling charges and things like that. So it's kind of a central optimization joint dispatch to minimize cost across the rail belt. So that's another thing that would have to change to kind of exploit the potential opportunity for lower cost electricity via joint dispatch. So we evaluated a number of wind sites. We let the model choose between the wind sites. It's basically choosing between the cost of wind, which can be less at better resources, but you also have to incur the cost of additional spur lines. You obviously may have transmission constraints. If you want to build a bunch of wind up north, you can only build as much as until you've kind of exhausted the ability of either GVA to use that wind, or the Alaska intertie to ship that wind down to the major population centers around Anchorage. So the way that the model choose between about 3 gigawatts of total wind sites that are shown on this map. The best sites are in the north and on the Kenai. And then since this is a cost optimization, there's costs associated with each of these technologies. And essentially, the cost of wind and solar is starting off between 50 and 80% more expensive compared to the lower 48. That drops over time due to a maturing market, but it's always at least 50% more expensive for wind, for instance, just because it's just more expensive to build stuff in Alaska. So all the costs of doing business in Alaska were adjusted. I don't think we've got really good numbers on how much it would actually cost to build wind in Alaska right now. So I think there's a lot of uncertainty there. But there is definitely it's much more expensive in Alaska than lower 48. The question is just really how much, especially when it's deployed at scale. So in terms of results, the key finding was that given the high price of natural gas, and the relatively lower cost of renewables, even with them being more expensive in Alaska, there's potential significant cost savings opportunity. Essentially, what you're looking at is the cost of gas-fired generation being around 10 cents per kilowatt hour. So just the cost of buying gas for the existing plants. Again, we're not talking about any of the costs associated with actually paying for the plant. Just the cost of buying gas for it is about 10 cents per kilowatt hour. And we're looking at being able to procure wind and solar for less than 10 cents per kilowatt hour in these cases, even with all the additional integration cost and natural gas storage, operating reserves, things like that. So the net of that is shown to the right. So essentially what's happening is you're paying a bunch of money for renewables, and you're offsetting a bunch more money associated largely with natural gas. And so every year by the 2030s, you're avoiding roughly $100 million in costs. And cumulatively, by the time you get to 2040, you're looking at over $1 billion of savings. That's not discounted. That's just the cumulative savings. If you want to calculate a net present value of that, you can apply whatever discount rate you want. So essentially, you're avoiding about $4.2 billion in fuel and other costs. And to do that, you have to invest $2.9 billion in renewables and other infrastructure. And now one of the big things here is the impact of the investment tax credit. We assume a 40% ITC applicable to both the renewable projects as well as spur line development. So that's an important potential cost savings that really is a huge driver behind these benefits. So the kind of mix, the big highlight is you're getting about 50% of your annual energy from wind in 2040. You are getting some from solar as well, but the big player is wind, given the relatively good quality wind resources and the relatively poor solar resources compared to the lower 48. But PV does become cost competitive, and so we do see some substantial PV development as well. It's really important to emphasize the continued role of the existing fossil and hydropower resources. These are all maintained to keep reliable operation. And as I'll highlight earlier, this is really critical. But there is a mix of resources, with wind being the single largest player. And in terms of where it's developed, the majority of wind is developed in the north and in the Kenai. The wind resources in the central region aren't as good. I want to note that the wind resource data that we had available to us is not the same as the developers are using. So we don't have the exact same wind locations. In some cases, we're not actually even considering some of the wind resources that are actually under consideration. So I think this is kind of intended to be kind of representative of something that might happen. But you can kind of see in the numbers in each of the boxes the total wind development. So you can see that there's a lot of wind in the GVA area and on the Kenai. And so that kind of tees up what we're going to see later, which is the significant use of transmission, particularly taking advantage of that upgraded Kenai intertie. So that really is going to be a big focus of the rest of the presentation. In terms, though, of the importance of the existing thermal plants and hydro for maintaining reliability, I think the central figure on this part, which is the reference case, this isn't a peak day, but it's close to a peak day. And again, there are going to be periods where the wind doesn't blow very much during some of these peak periods. So we're absolutely not relying on wind and solar to provide reliability. Wind and solar are acting as fuel-saving benefits only, and you're maintaining your thermal and hydro units for the purpose of meeting that peak demand or periods of low wind and solar. The other point, of course, is just how you're going to need to change how you operate these plants. And so you're going to have big swings in wind and solar output, where you're going to need to quickly ramp up your thermal and hydropower assets, as well as a lot of variation in the contribution from inverter-based resources. And so fortunately, I don't have to go over that. The ACEP folks and Telos folks had talked about this. One small difference is we don't go to 100% instantaneous contribution of IBRs. We have our hydro units, particularly Bradley Lake, have a minimum generation output. We do not turn them off. So, instead of 100%, we get to like 97% or something like that. Again, that's really the same, right? 97, 100. But that's the difference between. That's why we don't get quite up to 100%. But you do have hours of the year, many hours of the year, where you have extremely high contributions of inverter-based resources. And so we would need to address that through some of the mechanisms discussed in the ACEP report. And we include actually the cost of grid-forming inverters. We have a lot of reserves being provided by batteries, and there's a possibility of something like synchronous condensers, either adding new synchronous condensers, retrofit, using existing generators as synchronous condensers. So yeah, it's a nice complement, because you can't just take these results that I'm presenting without doing the stability analysis. Something would go wrong, but you kind of do them in tandem, and then you learn what is the right way of actually achieving this. So when we look at the role of transmission, kind of following what I said and what was said previously, it is really important that the transmission be used both kind of in a dynamic manner as well as just overall increased utilization. So this is an example of the flows along the Alaska intertie, based on understanding what's going on with wind resources up in the Golden Valley area. So the wind supply of wind in just that GVA area is shown in the orange line. So you can see it starts off at a little under 250 megawatts, which is actually more than the total load of GVA. So the net load, or what's the demand at GVA minus the contribution of wind, is shown in kind of the grayish line. So you can see that's kind of negative on the beginning of this period, which is November 4th, 2040. And so wind is basically supplying all of GVA's energy, and it's exporting on the Alaska intertie to the south. And then as the wind dies down, the net load in GVA increases, and they actually start importing energy from the central region. So that's the negative part of the black line. So if it's negative, it's importing electricity from the central region. This could be importing wind, or hydro, or this could be importing gas from the central region, because it's cheaper to run the gas plants than it is to run the oil-fired plants up in the GVA area. So I don't know exactly what's supplying GVA during these periods, but a big chunk of it is coming up north on the Alaska intertie. And then on the 6th, the wind just is blowing like crazy, and it's completely meeting all of GVA's net load, and it is what's left over is more than the capacity of the Alaska intertie. So the Alaska intertie is operated at its maximum capacity in the southbound direction, and you're actually probably curtailing a fair amount of the wind as well. So this just kind of shows that dynamic operation. You're swapping back and forth between northbound and southbound flow on kind of a regular basis. So that's one important part. And then just the increased utilization. So let me go back to the Alaska intertie. Let me go to the Alaska intertie first. And what we've got here is a duration curve, similar to what you saw earlier, that shows the flows on the Alaska intertie. So in this particular case, if you've got a positive number, you're flowing north to south. And if it's a negative number, you're flowing from the central region to the northern region. And we've got a 2024 simulated case. This is not actual. 2024 is not over yet. This is our simulated case. This isn't right, because it involves optimum dispatch. But basically, we're showing the Alaska intertie flowing from central to north, kind of in this optimum joint dispatch. And for the simple reason that the what we call the marginal unit, the unit that whatever is kind of meeting that any kind of incremental load in Golden Valley is an oil-fired unit, and oil is more expensive than gas. So it's cheaper to export energy from the lower cost, the really efficient combined cycle and reciprocating units in the central region that Chugach and MEA has, and exporting that into Golden Valley to displace that more expensive oil-fired generation. So that's what we would think would be an optimum dispatch today. But that switches as you start building wind. Then you basically are using the line many hours of the year, kind of over 3,000 hours a year. It's at full capacity, pushing that wind energy down into the central region. So that represents a pretty dramatic change in both how much the transmission line is used, as well as, again, the direction, the switching between north and south. The Kenai is a little bit different because Kenai is already being used to flow from south to north to export basically Bradley Lake energy. And so our 2024 kind of reference case, we're already using it, thousands of hours a year at its maximum capacity. But it's basically almost always operating from Homer up into the central. Not always. I mean, there's 1,000 hours or so where it's flowing in the opposite direction for various regions. But again, as we add more energy in the Kenai in the form of new wind, we greatly increase the utilization of the line, particularly even with the significant upgrades that we assume. So we're upgrading that line, the net line capacity of the lines, by roughly 100 megawatts, and we're still using that a lot. So this again shows the importance of transmission, both the existing transmission and potential new transmission, in supporting a renewable future that basically can offset these high cost natural gas fired units and kind of stabilize electricity prices with long-term fixed contracts. So I'll stop there and look forward to the conversation.
Great, thank you so much. And we are starting to get close to break. So we do have a few questions in chat, most of them, Paul, it looks like they are to you. I want to start, there was a question regarding one of your earlier slides, and I was wondering if you could just speak to it very quickly. I think it was either slide 3 or 4, and it was a question on how solar may or may not be included in the cost impact slide, and there was a question why that may be. Can you speak to why it may not be represented there?
The cost of solar, both the cost of solar included. So we've got the capital cost of solar, and then all the other associated kind of integration related costs. So the additional operating reserves, natural gas storage, the transmission interconnection, grid forming inverters. So all those costs are included in the effort.
Okay, thank you for that clarification. There was another question regarding the cost of plant and infrastructure. Could you please kind of explain the decision to maybe not include some of those as part of the cost analysis? There are real costs associated with it is the point of the question, and just talking through perhaps the justification of why the plant and infrastructure costs may not be included in those.
All plant costs of new plants are included. So any plants that are built between 2024 and 2040 are included in the analysis.
Thank you again for that clarification. How much land area is required for some of the proposed wind generation that you all are seeing in some of your proposals here? Is that land in a favorable wind area that's available reasonably close to the existing transmission system? Paul, I think you specifically had a slide that spoke to that quite a bit.
Yeah, we have a map of where the regions that we considered. So we do a land use screening. Whenever we do wind evaluation, we do a land use screening to make sure that land is actually developable. So it's not on like a national park or on somebody's farm or somebody's land. So so that there's a screening that goes on to make sure the land is actually developable. It also has like terrain restrictions. It can't be too hilly or mountainous. So once you've excluded those areas, then that might be available for development. So that's the map that I showed has those areas that are available for development.
Great, thank you, Paul. And Scott or Steve, and I did it again, Steve and Isabella, can you kind of talk about how that may have been taken into consideration for ACEP study as we considered wind? Again, the question is how much land area is required for your proposed wind generation? Is that land in a favorable wind area available reasonably close to the existing transmission system?
I don't have a perfect answer for that. I believe we followed the same basic procedures. Jeremy Vandermeer, our colleague, would know better, and perhaps if you really want to follow up, we could ask him, but I believe it's covered in our report. And I'm, let's say 99% sure that Jeremy and company went through the same kind of terrain and availability screening as Paul described.
And that brings up a good point. What I'll make sure to do, we're coming up on a break here. We're going to go over a little bit, but during the break, I'll make sure to link both studies in the chat for those that are interested in taking a look at it. I know you both had links in your presentation, but we'll put them in the chat as well. Okay, next question goes to stability studies. All of the stability studies appear to be consistent with operation security studies and not transmission reliability studies. How is the proposed system designed to operate in accordance with generation dispatches that differ significantly from the optimum production cost simulations used in the studies?
I think I can take this question. In one of the slides that Steve shared, there is a workflow of how the transmission studies where we land. So we start with the production cost analysis, and the transmission analysis, it is derived from there. So with the results of the production cost analysis, we get data for the entire year, for hours of the year, and this is where we select what I was calling the challenging hours. So we're gonna analyze all the hours of the year and define what are the challenging hours, would be the ones that we just have IBRs online. So basically the transmission studies comes from the production cost analysis. So when we have the optimum cost production cost analysis, we define the hour where we want to do the transmission analysis, which means that if this is the worst point of operation that the system will have in this proposed scenario, if we are able to make this worst case scenario reliable, we know that for other points of operation, when we have more inertia available, the system is going to be reliable. That's the idea. I hope that answers the question.
Great. Thank you, Isabella. Paul, did you have anything to add from your perspective on that question?
No.
Okay, great. So the next one, it might not be one that either of you can answer, in which case what we can do is also kick it to the IPP conversation we'll have next. But it's a question of what is the environmental impact of adding so many windmills? Does anyone have a take on that? Okay, Mike Kraft, I know you're on the line. We'll just plan on taking that in our conversation after the break. Next one is for Paul. We heard from Isabella about the need for properly developing the railbelt grid for stability. In your cost estimates, do you include the cost of those measures in your $2.9 billion estimate?
Some of them, yes. So in particular, the cost of grid forming inverters is included. So that adds a relatively small amount to the cost of the plants, but that's added. The spur lines, the natural gas storage, that's not really a stability thing. So some of the batteries also are included. So there probably would be some other things that would be needed. So and we talk in the report about if we're adding synchronous condensers, we kind of talk about what the additional costs of those might be. So those would reduce the benefits a little bit. So instead of like $105 million per year, they might reduce it to 95 or something $million a year. So there definitely could be some additional costs that wouldn't be included. So the benefits that we're showing would likely be less than what we showed, but probably not. I mean, they wouldn't be 50% less. You'd still there'd still be substantial benefits, even if you went to a full synchronous machine-based approach. I mean, grid forming inverters should solve the need for a lot of that, but there may be some need for some synchronous machines added. Yeah.
So I think that's a good segue into the next question, and it's talking about the cost of complexity. Are there concerns about the complexity of adding a lot of equipment that will have to be purchased, installed, operated, and maintained? Also, what is the cost of this complexity, which implies additional opportunities for system degradation or failure?
So the best thing that we can say is, I mean, there are a lot of places around the world that are doing this already. So Kauai Electric in Hawaii is a good example of a place that's already getting to 100% renewables. They're a smaller system than the rail belt, so they have all of the problems of trying to maintain stability in a small system. And basically, stability problems get easier as you get to bigger, especially frequency stability. So they're a small system that they need to spin up a gas turbine as a synchronous condenser sometimes when they're achieving 100% renewable energy. So there definitely is some of that. We added a additional cost of some of the scheduling and software needs. So we added an extra $1.5 million per year to support some of the communications and scheduling needs. So that definitely adds complexity. I think the real question is, what does that actually cost? And how much of that is, how much might it reduce the benefits of renewables? And so again, I think there's potentially some reduction there, but starting with kind of that $100 million a year type of number, it's certainly not going to add, you're not going to add $100 million a year in costs to address those complexity issues. So I think with reasonable confidence, given the experience of a lot of places around the world that are doing this kind of already today, given the fact that you've got some time to incorporate kind of lessons learned, this should be doable in a reasonable time frame and at reasonable costs.
Okay, great. Thank you. We've got 2 more questions, then we'll go to our 15-minute break. Existing debt seems to be excluded from the analysis. What would be the impact to the utility's ability to increase renewables if their existing debt is considered?
Yeah, that's always a concern. We're neutral on whether or not you go through a debt financing approach or a PPA approach, but my guess is that most of the new renewables will be acquired on a PPA basis, so there will be no new debt incurred by the utilities. All the debt would be incurred by the developers, and so they're the ones kind of taking the bank risk, and they're the ones who have to make sure that they've got good ability to get the credit. But you would not be exposing the utilities to any new debt under a PPA model.
Anything to add, Steve or Isabella?
Yeah, I think I'll just add that, and Paul can tell me if I got it wrong, but the existing debt gets paid either way. So it's a cost that it doesn't go away. It's not wiped off the conceptual map. It's just something that has to be paid down no matter what.
Yes, agree.
Okay, final question. This might be a little bit of a doozy and might not be. Can you give an example of a 100% IBR system with significant transmission that is in operation today?
I think Paul mentioned Hawaii. It's the first thing that comes in mind. And I think there are a lot of parallels that we can do with the Alaska system because it's also like an islanded system. So I think there are a lot of things that we can learn from Hawaii to apply in the Alaska.
Paul, any comments to add?
No, both the systems are small. You do get very high instantaneous contribution, in larger grids, but I'd be reluctant to use examples of other parts of the large U.S. grid that hit very high instantaneous contributions because it's just so much easier in those larger systems. It's just a lot more complicated in small systems. So I would focus on smaller systems that have achieved that level of renewables contribution.
Well, great. Thank you so much to Paul with NREL and Steve Colt with ACEP and Isabella Anselmo with Telos Energy. We really appreciate you sharing the report findings that you all have been working on recently. Again, I'll make sure to put the links to the studies in the chat. And with that, we'll go ahead and move to a 15-minute break. We'll see you guys all back here shortly. Thank you so much. Welcome back. Thanks again for joining us today. What beautiful music that we had during our break there. I hope everyone had a moment to stand up, get stretched, grab a glass of water, whatever you may need, or a coffee refill, as may be the case for some of us. So next up, we're going to have a facilitated conversation between myself and Mr. Mike Kraft, who's the owner of Alaska Environmental Power. We invite you to continue submitting questions in the chat box. For this discussion, we hope to integrate your questions into our conversation. We are going to be discussing managing variability and IPP perspective. Thank you for joining me this morning, Mike. Can you start off a bit this morning by telling us about yourself?
Well, sure. I live in Fairbanks, Alaska. I've been here about 45 years. I am the owner and operator of the Delta Wind Farm, company called Alaska Environmental Power. We have a 320-acre site in Delta Junction. We've been producing power for almost 14 years now. And we are limited currently to 2 megawatts. That's the Golden Valley Electric Association agreed to buy 2 megawatts, and that was the end of the conversation at that point. So we have been trying to expand this project for over a decade, and we are currently proposing a 34.8 megawatt project consisting of 9 3.8 megawatt turbines. We are fully permitted by the FAA. We are have an environmental impact study going back over 10 years that we also have in hand. We own the site. It is fee simple ground. So a couple of really good advantages in Delta. Number one, there's no property taxes. We don't pay a royalty to the state for wind use. We have quite the infrastructure in Delta Junction for supporting the development of this project, batch plants for concrete. We are on the Richardson Highway. Our point where we would take delivery on these turbines would come up the Richardson Highway through Valdez. Lots of contractors available to us to do the work, the foundation work and whatnot. We worked with Alaska Crane. The crane that we need is sitting in Fairbanks right now to install these turbines. And we're pretty much ready to go. We've entered into a RFP with Golden Valley Electric Association through Ameresco. Ameresco is the lead developer at this point. They're kind of taking the lead on it. And we have discovered that we have a pretty good wind resource in Delta Junction. I'm actually sitting here with one of the technicians that's worked with me for over a decade on the turbines. And, you know, we see a lot of turbines operating all over the world on a regular basis, the SCADA shots on them. And Delta Junction is right there at the top with almost any wind farm anywhere that we've looked at. That's Europe and America and Alaska. So we're pretty confident that we have a really good wind resource. We do know that at this point, after over a decade of production, we're going to scale up our wind turbines and use a larger rotor swept ratio, which will give us a bump in capacity factor. We often hit 126 consecutive hours of 92% capacity in the wintertime. That just happened in January. We see 85% of our production occur in the 4 coldest, darkest months of the year. November, December, January, and February are our high production months. We are anywhere between 55 and 70% capacity factors for those months, as opposed to June and July, where we drop down to about 17% capacity. So it kind of mirrors the consumptive rate of use on the rail belt grid. We are interconnected to Fairbanks with a 138 kV transmission line. Most of the consumers that we would be supplying power to through Golden Valley would be people like Pogo Mine, about 21 megawatts, Fort Greely Missile Defense System, another 9 megawatts, the pump station in Delta Junction, which is around 5 megawatts. So there's a lot of big consumers on that end of the system. And one of the things that's come out with us operating the wind farm now is we actually increase the efficiency of the system by about 2.75%. So that helps make things a little better. Other than that, I've heard a lot of questions today, and I really appreciate the opportunity to be here.
Yeah, thank you so much. And I know you and I talked about really wanting to focus on the variability aspect, but since just your intro there, we've already got a few questions in, and I do want to engage the audience. So let's ask a question that came in earlier. You were just talking about increasing some of your windmills that you have in your facility. Going to the question that we heard earlier, what is the environmental impact of adding so many windmills? Or what are some key environmental considerations? I think would be a good way to ask that as well.
Well, I think those questions really start at the beginning of a project, not necessarily 10 years into one, because the environmental impacts can be, bird migration routes and things like that. Bird strikes seems to be on everybody's mind. We have been very diligent about observing any kind of bird strikes. We haven't seen any. The one thing that I did notice that the environment in the wind farm changed. It was a heavily wooded site. And when we cleared it, we noticed that a lot of different animals moved into the site. Moose population increased on our wind farm. We've seen herds of 15 moose at a pop eating the willows that have grown up since we did our land clearing. We noticed that a lot of birds of prey are attracted to those open areas, hawks and owls in particular. We see a lot of those types of birds on the site that are hunting. We did a study in, I believe it was 2007 with ABR where they brought radar out there, and they said they could tell the difference between a pintail duck and a mallard a mile away with this radar system. So they were trying to figure out, what birds would be affected by our turbines. And we don't really see that at Delta because it is a flyway, but most of those birds are 2,000 or 3,000 feet up in the air. They're up there trying to get over the Alaska range by the time they're in Delta. They do land in Delta a little further to the east of us, but typically where we're at, we just don't see those kinds of flocks that are hanging out on the ground. So we haven't really noticed any real issues other than the change in habitat for moose and birds of prey.
All right, we have two questions in from Steve, but I'm going to get us onto the main theme here before I go to those. So our workshop theme is transmission and distribution, the clean energy transition secret weapon. Many of Alaska's renewable energy projects are being developed by independent power producers. In our conversation, we wanted to focus on managing variability. For context, could you explain what does that mean? What is variability and why does it matter?
Well, variability is better described as volatility because like today, for example, I'm having somewhat of a volatile day where my 900 kilowatt turbine, I've seen it go down to 200 kilowatts, which is where it's at right now, all the way up to 700. That's a pretty big swing. And so those are the kinds of volatility issues and variability issues that could relate to grid issues. There are ways to mitigate those impacts. And these are contractual agreements that can be made between the IPP and the consumer, utility, for example, where we can put a sit point on this turbine. So on a day like today where it's swinging all over the place, I can actually tell this turbine, hey, I don't want you to go above 300 kW. I don't want you to go to 700 and then back to 200. I'd rather see you go from 200 to 100. So we can actually program set points on the turbine to control that to some degree. That's curtailment. And so there are cases on days like today where you have volatility in the wind, where you would probably want to utilize some level of curtailment to keep that volatility down to a minimum. That's the easiest way to do it.
So what does that look like with your coordination with the utilities as you're managing your curtailment? What is the communication with the utility to make sure that they're able to accept that amount of power as you're able to curtail it and get it into the system?
Well, I think, the communications is going to be the key issue, between the dispatch operator at the utility and the wind farm operator. And on a project of 34.8 megawatts, we would probably have someone in an operations room pretty much 24/7 that can deal with these kinds of issues. And I would imagine that there would be days where, for example, I've experienced situations where the grid was unstable. And that would be high wind, for example, along the intertie where the lines are slapping, and there's other issues that are causing problems that result in a converter fault for me, because the turbine won't operate on an unstable grid. It will shut off automatically. It's a safety issue. So during times where some of these really abnormal events are taking place, it probably would behoove us not to run the turbine in those conditions, or an entire wind farm. If the system is not stable due to some kind of weather issue, then we would probably the smart thing would be to turn it off. And I have done that myself many times because I see that being a problem. At 2 megawatts, it's not really anything that rocks their system too hard. But what it is my turbine's coming on and off because these grid faults are are basically tripping the turbines off. And, we operate with the same, degree of accuracy that the utility, where we can only go 5% plus or minus on frequency or voltage or anything like that. We can expand those operational parameters on the turbine and absorb some of these wider bands of production, whether it's frequency or voltage, but staying within the allowed zone, we would turn the turbines off and keep them off for some period of time during that, and that would be communicated to the utility.
Great, thank you. So given the current grid infrastructure, in your opinion, what amount of non-firm power could be added to the system?
Well, I'm looking at this from a resident of Alaska and a resident of Fairbanks, and in particular, a resident of Golden Valley Electric Association. And so when I think about the fact that we are experiencing fuel shortages, both in the interior and in the Cook Inlet region, it just really it motivates me to make this power available, because we're not talking about how much it costs. We're not talking about the environmental impact of energy. We're talking about whether you even have it. And that came up in that Iceland discussion this morning, which I thought was very interesting. So when I think about how much can you put into the system, I would like to be able to at least put in enough to make up the fuel shortages that we are experiencing as a very beginning point. I think right now, I've served on the Rail Belt Reliability Council for 18 months. I've been involved in discussions going back to 2010 with the Gretzky discussions on consolidating the rail belt grids. I've had a decade of watching these meetings and listening to what's going on. And I think that there are a lot of opportunities right now without any grid improvements to be able to put probably in the neighborhood of 200 megawatts on the rail belt grid in various locations, like the Shovelhead Creek project, the Delta Wind Farm, expanding the Fire Island project, the Sleeping Lady project. And all of those systems would interconnect at a different place on the grid. And pretty much, if you're, my personal experience, if you're sending 78 megawatts from the south to the north, you should be able to send 78 megawatts from the north to the south. That system is there. And so if it's not being utilized, for example, if we're not getting economy power in Fairbanks from Anchorage into the tune of 70 megawatts plus, and if we had extra capacity of wind in Fairbanks, we should be able to send that excess capacity to people on the current system. As far as there's a bunch of reasons I picked Delta Junction. I've been a land developer my entire career. I've built 300 home sites here in Fairbanks, 50 houses. And when I pick apart a project as a developer, I look at, where the road's at, where the school's at, where's the power line at, all of these things that people want to have near their homes. And what's the zoning of the land, all those kinds of, what's the soil conditions, all those things that I look at building subdivisions and houses. I do the same thing with a wind farm. Where's the intertie? I'm 3.5 miles away from the Jarvis Creek substation. That's a 138 kV substation that connects me to the entire rail belt grid via the intertie between Delta and Fairbanks. That was a very positive thing. The wind resource. I looked at 4 different places in Alaska trying to find out where the best wind was. And I thought it was in Healy until I found Delta. And Delta was, the volatility of Delta was a third of what it was in Healy. We get these really strange conditions in Delta where these cold temperatures that develop in Northway present a higher energy density of the air. The air density increases, the temperature drops, and that air starts to flow along the Tanana Basin towards Delta, and it's out of the southeast for 2 weeks at a pop at 10 to 15 meters of wind. So I look for those kinds of things when I developed this wind farm. The intertie was probably the biggest consideration of all. I knew that was there. I knew that we were sending all the power from Fairbanks to North Pole, and I knew that could be reversed. I also knew that all those consumers were on that end of the system. So when you're looking at where do you put these things, you want to consider all those factors. If you're looking at a small project at your house, you might put a 20 kilowatt solar array on your house because obviously you have the interconnection to the grid to handle that. And you can use that power right at your house, without any improvements, without even having a second meter drop, you can do that. So I think there's a lot of room in the system right now to take a lot of beginning stages of what renewable energy looks like in Alaska without having to say, okay, well, we're not going to do anything until we spend $1 billion. I think that's foolish. We're already in a crisis. And by the time we get past building out this infrastructure to support 400 or 500 megawatts, like, for example, the Susitna-Wantana, even at 400 megawatts, we still needed to build power lines. If we were going to run a high voltage DC power line from the North Slope to Fairbanks, and let's say we sent 1,000 megawatts down here, which would be easy to do, we still have to build the infrastructure from Fairbanks to the rest of the rail belt in order to get that power through there. So, I'm not saying that those aren't great ideas and that that's not what the future looks like, but that doesn't have to happen right now in order to take advantage of opportunities that currently exist on the rail belt grid to bear, I'm thinking probably somewhere in the 200 megawatt range of renewables.
So as we look to the future, what do you feel does need to happen in order to support those projects to be developed?
Well, I think the first thing that needs to happen is we need to get really good at what we're doing here. And the only way we're going to do that is to get our feet wet with projects. Smaller projects like 34.8 megawatts in Delta. You operate that thing for a year or two. When you sit here and look at these SCADA screens for a year, you start to see things and you start to see advantages and disadvantages. And that's how you get good at integrating these renewables, is through practice. I mean, if you think about what's happened up north with the smaller grids, I mean, we've got communities up there now that are 50% plus renewables. That didn't happen overnight. They started out with used equipment 15 years ago and learned their lessons and moved up to the Northern 100s and learned their lessons and moved up to the EWT 900s. And now they're pretty solid systems. So, you got to start somewhere. And I don't think that, dropping an atom bomb to put a septic system in works very well. You're better off with a small backhoe. So, start with these smaller projects and get good at using them and operating them. And the other thing, too, that I don't really hear talked about is the fact that these newer turbines are pretty dang smart. There are a lot of things you can do with the newer turbines. Like, for example, the turbines we want to use are permanent magnet turbines. That means that you got the ability to use electrodynamic braking to regulate inertia. There are packages that come, control packages that come with these turbines where you can run the entire wind farm from one SCADA site, and you can control voltage and frequency and harmonics. And, so they're not as stupid as they were when they started out, where they just make power, period. They're either on or they're off. Nowadays, there is a lot of capabilities in these turbines to regulate some of these grid issues. And so I don't really hear that talked about very much. And then the other part of it, too, is just throwing out there the permanent magnet part of this. When you start looking at parasitic loads to keep turbines from cold sinking, for example, we operate down to minus 50 degrees Fahrenheit at Delta Junction. We've done it for a decade. And that took a little bit of forethought, because when we bought the equipment, it was only rated to minus 20. And so first thing we did was we changed the tower designs. We went to a different metallurgy. We used different bolts that are rated to minus 50. We figured out that on our yaw drives that we needed to put the little battery heaters that you glue on, not a 50 kilowatt forced air heating unit, but a 200 watt battery pad with a blanket over top of it. And so you can control these parasitic loads to keep these turbines from cold sinking. And the other thing that we learned was that the direct drive technology has a huge advantage in Alaska with respect to coal. We're not dealing with transmissions that have all kinds of fluids in them that have to be protected from cold sinking, the viscosity of the transmission fluid, and so on. So by going to these direct drive turbines with the AC/DC inverters, that is a huge advantage in operating at minus 40 degrees in Alaska. So those are some of the things that we learned from operating these turbines. And that's the kind of learning curve I'm talking about going forward with bigger and bigger sites.
Well, and that's especially important with your point that you noted that your highest power producing days are in some of the coldest days that we have in the interior. So I'm going to pull in some questions from the audience. Steve Colt is pulling in a question that came up as part of Guinir's presentation in Iceland. Mike, should we have a trading platform or continue to use long-term fixed price contracts for wind energy?
Well, I'm not really sure what the advantages or disadvantages of either scenario are. You know, we as an IPP knew that we had to come in with a project that was competitive and would entice the local utilities into potentially using renewable energy because, number one, it was cheaper. And so when we look at meeting the market, we tend to try and beat the market to some degree so that our product makes the top shelf as being used. And how you get there, I don't really think it matters. But if you can shave off some cost to the utility by providing cheaper energy in the form of displaced fuel, for example, I think that advantage is very clear to the utility that it's economically an advantage for them to buy power from an IPP at a cheaper rate. And the other thing that comes into play on these power sales agreements is, you know, one of the things that gets lost in the conversation a lot is the fact that IPPs, and I heard it said earlier, and I was glad to hear that, IPPs are the ones taking the risk. There is no public debt. We assume the capital cost, the development cost, we assume the operations and maintenance cost, and the liability cost for anything that we do as an IPP. Those are 4 costs that are built into the base rates of every utility customer in Alaska. And we just saw an increase in Golden Valley's base rate increase a couple of days ago. And so it's not just what fuel are you avoiding, but you're also avoiding, the public is avoiding all of these risk factors where you have a plant that either has a problem or doesn't perform right, or it increases your debt load. None of that stuff happens with these type of contracts with an IPP. It's essentially a fixed rate with some kind of an escalator put into it, and we assume all of the other responsibilities, including the interconnection cost, and that is not insignificant. Just to connect the Delta Wind Farm to the Jarvis Creek substation is about $5 million. So we're going to pay for that. We're paying for that 3.5 miles of power line. We're going to pay the operations and maintenance costs on an annual basis. We're going to pay the capital costs. We're also doing the development work, and that takes a little bit of time, and it's a lot of effort to develop a project.
And I think that becomes increasingly significant to understand because we heard in our last workshop from one of the utility CEOs that he did not necessarily see the future of power generation coming from the utilities. He did not necessarily see the utilities taking on those power generation projects and rather pulling in from IPPs. And that was again referenced this morning in our earlier presentation from NREL. I think Paul made that same point, is as we look to Alaska's energy future, especially renewable and clean energy sources, a lot of these are much more likely to come from independent power producers. And so that cost structure really does have an impact on rates. And keeping on the theme of rates, Steve has a follow-up question. As part of the ACEP report, there was an assumption that Alaska wind will cost 2 times more than lower 48 wind. Is that too high or too low or in between?
I don't agree with that. I mean, it comes down to which contractor are you hiring to build your house? Are you hiring the guy that shows up every morning and is part of the crew, or are you hiring a guy that subs it out to 4 other people? A lot of these projects, like, for example, the one I'm doing in Delta Junction, I'm the guy in the bulldozer clearing the land. I'm the guy in the bulldozer building the roads. I'm the guy that's ordering the concrete. I know the guys that make the concrete. I've been working with them my whole career. So, I mean, I'm able to bring to bear my experience as a developer and a builder to limit the cost of a project by being efficient, by doing it one and done, not having to tear stuff apart and rebuild it, not making mistakes. The cost of building a wind turbine, I think if you ask for a quote from, I'll just throw Intercon out there, even though they don't do business in America. it doesn't matter whether I'm calling from Puerto Rico or Fairbanks, Alaska. The price for a turbine is the price for a turbine. Now, the difference is, how do I get it here? Okay. So if I research the best way to ship that turbine to Alaska, and I come up with the most economical way to get it here, that's another opportunity for a developer to shave some of those costs, like bringing it in through Valdez, for example. I would not bring a turbine to Alaska in the middle of the summertime. I would bring it here before breakup, when the roads are hard, when there's not a bunch of traffic on the Richardson Highway, and I can get those trucks back and forth at 278 miles without having 4,000 other vehicles on the road. I don't have to worry about the load limits. I'm not stalled somewhere for 2 months with a bunch of equipment sitting somewhere doing nothing, waiting for the load limits to come off. So, I mean, organization is a big part of cost. And, you know, concrete costs more here for sure, but it's not insurmountable. Rebar for the foundations costs a little more here for sure, but, you know, that would be the case no matter what you're building. You're going to pay a little bit more for that stuff to get here. But I don't think it's that big of a difference, to be honest with you. Transformers, for example, I would be getting these transformers out of Saskatchewan, Canada. They would drive them on a truck right to Delta Junction, come up the Alaska Highway. That's a kind of cost-cutting measures that you can use as a developer to try and keep your development costs down.
Great, thank you for that perspective. We have the next question is, how long would renewable energy expansion take? Right now, we are set to experience a natural gas shortage in South Central Alaska, starting as soon as 2026 and 2027. As a developer, can you get enough energy online in such a short time frame, including permitting and construction?
The short answer is yes. We've been ready to put this online for a decade. Okay, so we could have already been operating, and this shortage wouldn't be as big as it is. But here's the problem: if you're a builder in Alaska, you learn pretty quickly that you better have your act together in January if you're going to build something in June. Okay, because there's certain things you have to start in January in order to be able to get all of your equipment there, all of your supplies, and be able to complete that project before November comes around, because that's the day that the cost doubles. So you don't work in November and December and January. You have to do your work when the weather permits. And the other part of it too is the wind farm, you start to put people in harm's way. The longer you go into the fall season, the windier it gets, the colder it gets, the more dangerous it becomes. So, you know, our plan of approach was to bring those turbines up early before breakup. We were going to do the work this year. We are fully permitted, including the FAA permits at Delta Junction. We could have been online not this September, but the following September, with ordering the equipment and getting it here. The last thing you want to do as a developer is order $40 million worth of equipment and then watch it sit there on the ground all winter long, waiting for the weather to break. That is just not going to happen in the private sector. So timing is everything when you start these projects. And if you miss it by 1 week, you've lost a year, an entire year. And that's where we are right now. We've already lost 1 year of being able to bring this project online, not this September, but the following September. We cannot make that happen at this point in time. So we've lost a year at waiting for a decision. We're ready to go. And the project, you know, if you look at other projects, you know, I don't pretend to know everything about Shovel Creek, other than the fact that, you know, there are certain milestones you have to get past. You have to do the environmental impact. You have to kind of figure out, okay, what's that going to look like? You have to find out what the community wants, you know, and there's been a lot of rhetoric from the community about that particular site. You have to figure out what the land leases look like. You have to figure out what royalty agreements look like, what the property taxes issues are. There's a lot of milestones that they still have to get past to get to the point to where they can actually apply for an FAA permit. That opens a whole nother can of worms, because that could take 2 years just getting an FAA permit for a hazard to navigation issue. So, you know, it varies. The development time varies on each project depending on on how close to the population you are and so on. In Delta Junction, we're looking at 30 square miles of agriculturally designated property with an incredible wind resource. So to be a wind farmer in Delta Junction is not very different from being a potato farmer. We're going to change the landscape, and we're going to be there for a long time, and we're going to produce a product. And so I think Delta Junction was particularly well suited for that type of development. I don't know about some of these other areas that are being talked about with the folks. I do know that we tried to put up a med tower in Houston, Alaska, and it was made very clear to us by the Houston City Council that they don't want wind turbines in their community. So guess what? We didn't put up a med tower. I'm not going to fight that. That's what that community doesn't. They don't want it. They don't want it. So you've got to be willing to walk away from projects as well if you're not going to have consensus. And I just think that it's so important that we take these measures to make up these fuel shortages as quick as we can, because I as a developer, a land developer, I see a big blank here now where I'm concerned about people leaving my community because of energy costs and the availability of energy. And I think the same thing has happened in Anchorage. So anything we can do to stave those kinds of conditions off of our economy, we should be doing. And wind is currently, I think, probably solar is probably the fastest one to put it online. But wind is not too far behind it. It's certainly faster than a new power plant of some, hydrocarbon power plant.
Yeah, that's interesting. We've heard, even with our Iceland conversation this morning in regards to hydro, how, communities are really making it clear what sources of projects and where the energy is coming from is important to them. And that's influencing the project decisions as you move forward in the futures and the different perspectives. So that's interesting. We've gotten a couple questions here in regards directly to the barriers that you're experiencing with moving your project forward. One asks, what can the state do today in order to get it up and running? And just another is just asking for more clarity on what the barriers are. I will say we're about at time, and there were two other questions I was hoping to get to, so we'll go a little bit long, but I want to give you a chance to talk about what those barriers are before we move on.
Well, I think the state of Alaska has done everything it possibly can to develop renewable energy in Alaska. I mean, going back to 2010 when AEA was established and the Alaska Energy Fund was established, and they gave grants out to develop this technology. They did that, and they were very successpace at it. Look at what's happened in the state. We have wind turbines all over the state now, and solar arrays and so on. We're even talking about space heating now with excess power from turbines, which was never talked about 5 years ago. So the state of Alaska put hundreds of millions of dollars out there to develop this technology, and they did a great job of it. The problem has been where the tire meets the road on the rail belt. The utilities have been somewhat reluctant to work with renewable energy IPPs or develop their own systems. And I'm not sure why that's been so hard for them to see the light at the end of that tunnel. But for whatever reason, they've been pretty fixated on coal, gas, and oil. And not really sure why that is. It doesn't make sense to me why you would, bend over a $10 bill to pick a dime up. It just, there's opportunities to save money. And here in Fairbanks, it gets a little deeper because we have a severe air quality issue in Fairbanks. We're the third most polluted cities in America with respect to air quality. And a lot of that is source point issues, not only wood heating and cars and homes, but also source point. So we really have a couple of good reasons to do this. One is we save money. The other is it's cleaner and our air quality improves and it's sustainable. And that's the other part of this that I don't guess I realized when I started building wind farms, that a kilowatt hour of power coming off a wind turbine is pretty damn harmless compared to what happens with the oil industry around the world. Whether you look at Nigeria or Venezuela or some of the other places where people are actually being, essentially killed over it, and the battles that go on in the Middle East, and the fact that right now we're worried about tankers being blocked in the Suez Canal, all those issues go away because the resource is in our backyard. We have total access to it, total control over it. we get to utilize it to whatever measure we want to. We don't have to worry about what happens somewhere else in the world and how it affects our energy cost or even the energy availability issues. So I don't think I ever realized that when I started out, but a lot of energy security comes from having these systems in your own backyard, in the service areas that, like Golden Valley service area, for example. Golden Valley has access to it. If they don't want to use it, then they can sell it to somebody else. Maybe it's another utility down the intertime. But that's a very strong point for me personally on a moral level of why renewables are also such an advantage.
Well, we'll be having a panel next that talks with some of the utility members with their perspective. So we'll be able to dive into some of those questions there as well. So 2 more questions. We had one come in, and then I want to get to the question on wheeling rates that we discussed. Have you found IPPs working together to achieve a sort of communal economies of scale, either here or elsewhere? If so, how do they do it? If not, how can we effectively build such a community to procure, build, and power together?
Well, when we realized what we were up against with respect to doing business on the railbelt grid or even doing business in Alaska, we formed the Alaska Independent Power Producers Association. We're 13 members. We're still out there. And we started advocating down in Juneau for certain things, that we thought would open these markets to us. And currently there are probably half a dozen projects across the state, projects like Sweetheart Lake in Juneau, for example, or the expansion of Fire Island, the expansion of the Delta Wind Farm, some of the solar projects that have gone in. All those people are members of the Alaska Independent Power Producers Association. So our focus has been on market access, not necessarily that we have to work together and pair projects or that we gain some value from a larger consumer of concrete or whatever. It's been more about the issues of access to the system with our products. That's been the real discussion that's going on in the state of Alaska with respect to IPPs working together. That's been the focus.
So not necessarily coming together for project development, but more working together to make sure that as projects are developed, how to get them delivered into the system.
How to get them online.
Good to know. So I want to close out the conversation today. We've heard a lot about wheeling rates just in conversation generally as we talk about Alaska's energy future. Can you explain what wheeling rates are and how changes to wheeling rates support broader diversity of wind power and other cleaner renewable energy projects with transmission over service areas?
Well, I'll give you the one example I know really well is Bradley Lakes. Fairbanks has a portion of Bradley Lakes. I think it's 15%. And that power is wheeled through Homer Electric, Chugach Electric, MEA, across AEA's portion of the Northern Intertie and into our service area. Every time it crosses a border, it has a price tag. And that is the wheeling rate that is charged by that utility under 2 scenarios. One is regulating the power flow. The other one is the actual, just the transmission of that electricity across those power lines and what does it cost to do that. Those are what the wheeling rates are made up of. There's two parts to it. Currently, it's been, we were at a point in time probably 5 years ago where we would have been better off selling Bradley Lakes to Homer for some amount of money and spending that on fuel in Fairbanks and making our own power up here with the money we got from the power that we sold for Bradley Lakes, because it would have been cheaper. We'd have made out financially by doing that. But we couldn't have really, when you get 5-cent power and all of a sudden it's 14 cents when it gets to town because of these wheeling rates, that kind of kills the economics of that. And a lot of that came down to the fact that you had, at the time, 6 different utilities on the railbelt grid. Now it's down to 5. And there's currently legislation being talked about in Juneau that would postage stamp that, so that no matter where you were on the system, you paid a postage stamp rate. And if Shovel Creek was making 100 megawatts and we only needed 50, that means that they could send 50 of it either to Chugach or MEA or wherever with a postage stamp rate on the transmission of that power. And that would be very helpful, because these pancake rates pretty much kill the economics of wheeling power very far across different systems. So I'm excited to see that is being discussed in the legislature right now.
Great. We are a bit over time, and I just wanted to thank you so much for joining me today. Look forward to continuing these conversations and really appreciate your participation. So with that, we'll move on. I'd like to welcome our next panel. I know most of them were here for some of that conversation, so I'm sure some of it will seed our conversation. We'll be talking about integration from a utility planning and transmission asset owner perspective. We just heard the IPP perspective, and now we'll move to the utility and transmission asset owner. Once energy is generated, how is it transmitted and distributed? I'm pleased to be joined by Bill Price, who is the Senior Infrastructure Engineer with Alaska Energy Authority, Ed Jenkin with Matanuska Electric Association, and Dustin Hires, VP of Corporate Programs with Chugach Electric Association. Thank you so much for joining me. Bill, I'm going to toss it over to you first, just to take a quick moment to introduce yourself, the Alaska Energy Authority, and the role that you play over there.
Bill Price with the Alaska Energy Authority. We do a lot of things. We own Bradley Lake. We own some transmission equipment. We also support hundreds of utilities around the state who kind of stand alone in the villages, so to speak. I've done work in the villages. In the last few years, I've been working on the utility, on the rail belt side as an infrastructure engineer, trying to support it as best I can, and happy to be here.
Great. Thank you so much. Mr. Jenkin with Matanuska Electric Association, you mind introducing yourself and MEA?
Well, hello, everybody. I'm Ed Jenkin. I am presently the Chief Energy Transformation Officer at MEA, which means I work with a team of people that in a partnership to develop renewable energy products or other projects for MEA to assist us in meeting certain goals, renewable or clean energy penetration on MEA system. MEA has a goal of about 50% by 2050, and that is what we're working toward right now. Thank you.
All right, thank you. And Dustin, over to you with Chugach Electric Association.
Good morning, everyone. Dustin Hires, VP of Corporate Programs at Chugach. I'm in charge of the decarbonization program for Chugach Electric. That puts me in charge of all the renewables, trying to get find a path to get all those renewables onto the system, get some clean energy on our portfolio. For my background, I've been at Chugach for over 20 years, spent most of that time in power generation, and was recently pulled over into this job in order to start working cross-functionally across all our divisions to try to make this happen. And of course, we're working closely with our power pool partners at Matanuska as part of the power pool. And we're happy to answer questions this morning.
Great, thank you so much. And I am not the technical experts, so thank you so much for helping me with some questions to shoot your way to get us started. And audience, please, as we've been doing, continue to use the chat to submit your questions, and I'll be weaving them into our conversation. So I leave any of these up to whoever speaks first to do the answer. Please feel free to have all of you answer if you have different perspectives. So can you start us off with, can you please define what N1 means and why it is important?
N minus one.
Is it N minus one? My apologies.
N minus one. It's kind of a phrase used in utility circles. In the villages, that translates to one. You need one engine to operate. You need one engine to back that one up, and then you got to have a third. So when your oil, simply stated, if you're doing an oil change, you can't have the lights go out just because you lost the other engine. So it's backups after backups. I'll let Ed or Dustin go into the utilities, and they can do a lot better job speaking at a utility scale than I can.
Well, I'll tackle it and just say N means normal. So when we say normal minus one, it means something has happened on the system to remove something from your system that normally is there. So utilities plan for contingencies. So when we say N minus one, that means we're planning for normal and then the removal of something on the system. So typically, substations have capacity so that if the substation next to it goes down, we can still serve load, or transmission lines have multiple paths between areas. If the transmission line goes down, we hope to be able to still serve power. We know in Alaska that's not the case sometimes, because when we're trying to power up to Fairbanks, there's only one line. When that one line goes down, we have no other path. So in those cases, you fail this 10-1 criteria we try to meet.
Ed was talking about transmission lines. Here in the central area, we got transmission lines to the north and to the south. We might take an N-1 on one of those transmission lines, and we might survive. And if we take another hit on the other transmission line, that's an N-2. And we have to design our systems accordingly to withstand those kind of conditions.
Well, that was a great example to really demonstrate what we were talking about here, whether it was planned or not. So moving on, can someone describe what reliability standards are and why they matter? Are there the other types of standards to be considered? Whoever wants to start. Dustin, I'll throw it at you.
Oh, reliability standards are kind of an interesting little game here. I think Ed, as the electrical engineer, is probably a lot more capable of answering this, but I'll take a shot. I took a look at it. I came up with 10 different categories of reliability standards. The most popular one that we talk about routinely are the BALS, or balancing authority type of standards that we enforce. The ACEP standard was introduced based on the national standards, so we do have standards in place that we need to adhere to. So you have balancing authority, critical infrastructure, communications, emergency preparedness and operations, facilities design. I'll just throw it in there that's got personnel performance, protection and control. I mean, there's all these different elements to standards. And I think it's important to point out that when you're modifying or touching those standards, it really has a big implication to the routine operations of the utilities and the cost of operations.
Ed, it sounded like Dustin was setting you up to expand upon his answer there.
Well, he listed them all off pretty well. So in general, we have standards to make sure that on the front end, we can actually model the system. We have modeling standards, as Dustin said. So when a generator is put on the system, when a transmission line is put on the system, a substation, those are put into a model that we can actually run and verify system operations and confirm that the system's responding as we want it to respond or expect it to respond. I mean, Dustin mentioned balancing, and that's because we talk about balancing frequency to load all the time, because frequency and load have to match every second. So we have standards that tell us how we have to operate the system to maintain that balance, even under contingencies. So there's a number of standards that basically direct us how to model, how to plan the system ahead so that the system meets all the requirements in planning standards, and then how to operate the system to ensure that it's as reliable or meets the standards for reliability based upon those accepted standards.
So Bill, I'm going to toss this one to you. What are some national standards that are addressing the interconnection of non-dispatchable or IBR resources?
There a lot of, I'm going to have to lean on Ed to help out on this as well, because I'm a mechanical engineer by trade, so I'm learning a lot of this. But there's a difference between there's the standards that we have here around the intertie that are explicitly agreed upon by the multiple utilities, have spent hours and hours and hours negotiating and working out what they need to do in order to play nicely together on the same wire. And then there's other standards that are put forward by entities such as IEEE or other entities that put a standard out here that if you want to do this, you need to do this in response to it. One of the standards that's being discussed is IEEE 2800 with respect to IBRs. And I'm vaguely familiar, not vaguely familiar with it, but I'm going to defer to Ed to explain that, or Dustin, much better than I can, rather than me fumbling over words.
Hey, for the record, I'm right there with you, Bill. I'm a marine systems engineer. So Ed is our resident electrical engineer. I know he's got a good grip on this stuff.
Sounds like the pressure's on, Ed.
Yeah, that's what they like to do.
Sorry to interrupt, but the next question too brings it up. I'm sorry to skip ahead a little bit, but
okay. So I think there's NERC, right? So NERC is really the overarching keeper of standards for the lower 48 because all those states are interconnected, and therefore there's a federal oversight there where places like Alaska and Hawaii don't have NERC standards. And part of that is because we don't have the level of interconnection, we don't have the level of load, and honestly, there's things in NERC that we probably can't afford to meet because we don't have such a stiffly held together system. But what NERC is doing is, they've looked at inverter-based resource performance. They've put out a finding that, we consult as far as a level 2 alert concerning IBR activities and responses. We'll probably follow them in the work they're doing that's revisiting the modeling standards. And as well, they're redoing some of their transmission planning standards. And we'll probably let them take the lead on that and then follow them along as they have a lot more technical input and a lot broader base to pull on for those standards. I mean, Bill mentioned IEEE 2800, which establishes a uniform set of technical minimum requirements for interconnection, capacity, and performance of inverter-based resources. So that's something else that we'll probably be taking a very strong look at and maybe even adopting it in Alaska. I mean, that's some areas have already adopted IEEE 2800. And now they're coming out with a modification supposedly this year. So, and then even DOE gets into the act. I mean, they've put out publications because we are all right now trying to dip into Department of Energy funds to help, improve the system. And they've got some documents that they've got out there that require us to use verified models for inverter-based resources instead of just relying upon vendor-relied models for determining how the system's going to respond. So there's a lot of people out there working on standards. I guess what I'd like to say out of that is it's not an Alaska problem. It's not even just a USA problem. It's an international problem. You have a lot of people that are addressing standards to facilitate the system moving towards a different type of generation scenario, using different type of generation assets and helping us maintain reliability.
And we have had a couple questions come in what NERC is, and it is the National Electric Reliability Corporation. So just to North America Electric Reliability Corporation. Thanks for that clarification, Steve. Okay, and I actually am going to take a question from Steve. Earlier this morning, we heard from Ginir from Iceland, and he was talking about how they are looking towards a trading platform for wind projects and in order to get wind projects into the system. Is that something that Alaska should consider in order to increase our wind energy procurement, or is the fixed contract system that's currently in place the best way to move forward at this point?
Good question. I'll jump in. I think the silence speaks loudly. As far as our rail belt goes, I don't think we've ever contemplated a market type system where people can get in and do like a trading type of operation. We're just now, and I think Mike Kraft said it a bit ago, we're just now getting into the industry. We're just now starting to bring on these types of projects. The future is wide open, but for now, I don't think that we're in that game yet. So maybe Ed can expand on that or maybe amplify it.
Well, I think another thing that's been talked about is because of our single transmission line and those constraints, sometimes we have constraints on the system where one entity can take a resource that another entity can't. So I wouldn't call it trading, but I would call it a cooperation amongst utilities and discussions about potential purchase agreements that take into account those potential constraints on the system and the need from time to time for us to, I don't think trade's the right word, but for someone to take a resource they have access to for some period of time and then offset it with a different resource. And those are things that have happened in the past and things we'll continue to discuss as we look at how to bring on larger regional projects onto the system.
All right. So earlier today, we heard from the ACEP decarb study as well as NREL's study in regards to the rail belt transmission system. And we have a question here. Are the transmission lines between Kenai and Anchorage and Willow to Healy thermally limited or stability limited? And what is that difference?
Bill, I'll let you jump in. That's your transmission line between
Well,
Willow and Fairbanks. Healy.
For thermally limited, meaning you can literally, you're limited on how many kWs you can push across that line before the line gets too hot. You're limited, you're maxed out. Stability limited, meaning if you push more kWs across that line, you start tripping things out because of system stability, the frequency that Ed mentioned. And both of our lines, I think, especially the Southern Intertie, both of them are actually stability limited. We can't push lines, and it's mainly because there's only one of them. You can only push, and you only push it so hard before you get to the point where you're out of balance. You've got too much load on one side to another, and I'm getting a little out of my depth into exactly how that dynamic works. But what happens is you end up with oscillations where one engine's trying to match another frequency on the other end of the line, and it becomes difficult to get a stable frequency. And as the frequency goes further and further out of sync, you end up dropping generation because the generators protect themselves, and then you start having outages. And so, in short, it's stability limited.
Ed, did you want to add to that?
Yeah. I'll add just for the fun of it. I've been in dispatch center where the line from the Kenai, not thermally limited, but because of other failures on the system, was pushing up more power up into Anchorage than we wanted. And at some point, because of the high impedance, basically the generators on the Kenai go out of step from the generators in Anchorage, and that line trips out. And it's just solely because of how the impedances and voltages change as you push more power over that single line. That causes an instability on the system. So, but I think that was the last time we blacked out Anchorage. So that's been a few years ago now.
So I think that leads us into a great question from the audience here. Can you speak to the stability challenges that wind and other renewables introduce to the transmission grid that speak to the need and cost of technically integrating them into the grid? Dustin, you're nodding your head the most, so straight to you.
I was absorbing the question.
I can repeat it if that would be helpful.
Well, I think really what it comes down to is bringing on this amount of variable power. I think Mike in the earlier conversation was talking about dipping our toe into this, bringing on relatively small amounts in order to get comfortable with it, get some experience with it. That's absolutely I think a smart play. The question is, how far can you bring on variable power, and how much can you bring on, and where? These are the questions that really start transitioning from what ACEP, NREL are doing from this capacity expansion modeling, this production cost modeling, regime into the power analysis side, where we're trying to figure out when you bring something like that onto the grid, what is its impact going to be? How is it going to be interconnected? How is it going to play with all the other systems? And it's not an easy answer. It's actually a very complicated answer, and that's why it takes so much time and money in order to get these studies done. So I think I'm touching on the answer to the question, but maybe I'll turn it over to somebody else to try to pick it up from there.
Bill, do you want to expand on that?
Well, if you can visualize, if you've got in the lower 48, they have what's referred to as an infinite grid, meaning it's theoretically infinite. Up here, we're clearly not. We're an island. And if you bring on, and you can only, when you have a variable source of power that could drop out, the wind could die off, the clouds could come over, things change, the system can respond by either responding with more generation or less generation, or it drops load shed, or you lose power, or you have an outage. And our standards define when we're allowed to drop load and those sort of scenarios. And the clouds coming over at our generation source is not one of those options. And so what you end up with is the higher you need to be able to have generation online to support the potential loss of that generation source in a backup sense. And as that penetration increases, that load penetration, that percentage, the more difficult that challenge becomes.
Thank you. Ed, anything to add to that conversation point?
Yeah, I'm just going to try to make a distinction between how we operate the system and the stability of the system. Because the stability of the system really has to do with what's flowing on the system and when, and how we respond to faults on the system, and does the system stay together. So part of the issue is, where do we locate facilities? How does that change the power flowing along transmission lines? And how do we plan for those changes? And can we do that in a way that we can survive an N-1 without going unstable? The other issue being discussed here as well is, how do we regulate? How do we follow non-dispatchable resources with other generation resources? So as they change, we have other generation resources online to make sure we can properly follow those resources to ensure that load and frequency already match. So yes, there's a stability issue that has to do with where stuff is located, how big it is, how much power is flowing, but there's also this other issue we're studying and talking about here, which has to do is, how do we regulate the system to ensure that we can maintain frequency and serve all our members, no matter how those resources that we may be putting on change.
So we're really dipping our toe into studies. There's a lot to learn. So what is a transmission study, and what are some typical integration studies, and why are they required?
I guess I can start. So interconnection of any generation facility, whether it's an IPP or a utility-owned facility, there's various studies that we do. Some of the stuff we've talked about is, basic power flow studies, so we can identify if that resource is put on the system, how do the flows on the system change? And does that impact any of our limits based upon stability or meeting N-1 criteria? But then we also have stability studies where we look at, what happens if there's a fault on the system and we lose this transmission line, and, the fault brings voltage down to 0 on this section of the line, and how does the rest of the system respond? Does it maintain stability? We have interconnection studies that talk about, what's a reliable mechanism by which we can interconnect these facilities. We do voltage studies to, identify what changes on the system with respect to voltage security do we have on the system during when we add this new resource that provides a different level of voltage support. And then there's the regulation studies that we've been talking about most of the time with respect to non-dispatchable resources like wind and solar. How do we operate this? And how do we maintain security to load? So there's a bunch of studies we do, and hopefully that also tried to hit the highlights on why we do those studies. But
yeah, so we have a question. Oh, go ahead, Dustin.
Yeah, I wanted to make sure that we hit the high point about regulation studies. Up until recently, whenever we added a new generation source, it was typically something we could control. In other words, we didn't have to put a lot of effort into understanding how it was going to act on the system because we can tell it how to act. Whenever you bring new resources on, like variable resources like wind, solar, and things like that, now you can't control that anymore, and you have to figure out how to make those other generation sources and other energy storage sources respond in order to keep the grid stable. So this idea of a regulation study is a relatively new concept, whereas we didn't really have to deal with that before. I just wanted to point that out, that the studies that we do have had to evolve in order to accommodate this new era of clean and renewable energy.
And Brittany, if I can jump back in, and we look at variable mechanisms by we can regulate, because part of our goal is to figure out the least expensive way we can regulate and bring this resource online to do it in the most economic manner. So thank you.
One other quick point I'd add on the IBR or the wind or your solars, where we have three regions connected by one single line, an extension cord. It's the more IBR penetration you have. Say, for example, Golden Valley gets a bunch of new wind turbines, and they're running mostly on those wind turbines, but their foundation is a bigger load in Anchorage, and they're sourced to that. If the intertie trips out, Golden Valley now goes to a very, very high penetration level of wind, loses the anchor they have in Anchorage, and you potentially, I'm butchering this a bit, but you at Fairbanks would potentially go out because they're not set up to handle that dynamic of losing that reference point in Anchorage and losing that I'm kind of butchering it a little bit, but that's what the studies are there for. We're running hundreds of scenarios and different things that can happen, different scenarios, all of those different things to try and figure out, if this happens, then this. What happens here? How do we manage these issues? How do we prevent large-scale outages? How do we prevent loss of generation for various reasons?
So, Brittany, I think we can take that back to your very first question, N-1.
Yeah.
Yeah. So if that tie goes out, and in that example that Bill gave, all right, Fairbanks now has an N-1 condition. You have to deal with that, and it has to be designed to accommodate it. So on electrical systems, just across the board, you don't design to what usually happens. You design to what might happen, what can happen, which means you have to accommodate all of these different conditions.
So I definitely understand the role of the studies, especially as we're on a learning path on how to integrate these. We have seen RFPs come out from utilities for various projects. Can you explain the relationship and how, what comes first, the chicken or the egg, right? So you need to do some studies, but at some point we need to dip our toe in and start moving forward on these. So can you explain why an entity may move forward on an RFP prior to studies being completed, and maybe an example of when we can't move forward on something until a certain level of study is done?
Sure, I'll jump in on that. In 2021, in 2021, Chugach issued the RFP for renewable energy. We got 12 responses, only 2 of which were kind of borderline economic, according to the current avoided cost. So I kind of wanted to point that out because whenever we have this discussion about the cost of renewable energy, yes, we can theorize about what the costs are, we have direct experience that says only 2 out of 12 projects actually even approached what might be economic according to the Regulatory Commission of Alaska. So we had to first put out that invitation to get that information, figure out what those projects look like, and then with that information move forward on what we might do with that information. So we have capacity expansion modeling. That's kind of a roughed in version of that, saying what might we do, how might we expand our models. We have to do production cost modeling, figure out when we integrate this from just an energy basis, does it look right? Can we see the other shore from, on the other side of the river? And then we have to get into the other types of studies, interconnection impact regulation studies, that say, how are we going to get there? In other words, it's not enough just to say that it's economic. It's not enough to say that the brass ring is there. And as we saw on the front page of the newspaper the other day, $1.3 billion in savings by 2040. Yes, that is absolutely a driver to go this direction. The utilities now have to get involved and take it to the next level in order to figure out how the power is going to flow on the system in order to make sure it does not black out the system. We have to figure out what those stepping stones are across the river in order to get to the other side and get that payoff.
Bill or Ed, anything to add to that great description?
No, one thing I saw, one of the questions is the RFP question is, and utility staff lean heavily on outside contractors due to their experience level and their understanding and their skill level of just doing studies, whereas the utilities focus on more operations and maintenance and not so much spending all of their capital on studying problems. As to why there's so many studies, it's every single subtle change could warrant its own new study. And not only do the standards require that you know what's going to happen before you plug in this new power plant, the just good engineering answer says, I need to know what happens when this runs. And many of the models, many of the systems that are out there to support these studies are still being developed. Many of them don't do what they're supposed. Many of the IBR studies doing grid forming inverters and all these different things, the models being used don't accurately represent what actually happens in the field all of the time. That all has to be back checked. That all has to be, basically you got to let the engineers figure it out at some point. And a lot of the things that have been put out there, a lot of the scenarios that have been presented as to how do we solve our problems in Alaska, we've got a proposed solution here, we've got what we think it's going to cost here, and the engineering in between has yet to be done. And that's the part we're stepping back as utility owners and as infrastructure owners, trying to say, how do we get from A to B? And the first step is study after study after study.
And then to add more studies to it, we're really talking. Ed, were you going to expand on that? It looked like you were about to say something. You're muted.
Well, that's because I didn't want to interrupt you. Well, we do resource studies. So we do those on a frequently basis, and that identifies, as we use experts out there who are experts in pricing and resource costs and what that is. We do resource studies, and we look 20 years out. And we look, how is this resource going? How is this expected, this resource to what's it look like 10 years from now? What do we think? And, a lot of that is NREL. We use a lot of the NREL work for a lot of the pricing, but we also have current pricing that's significantly different than NREL's in some cases. So that's a study we do that helps us determine what we want to look at and what type of RFP we want to put out and who we're looking at and what time is it to do when. So we do resource studies to give us some future direction. And then, as Dustin said, you put out RFP, you put out something at 2021, I think Chugach did, to get results, to get input, and then that project is a unique project. And that unique project requires how is it going to be interconnected at the specific location? Because when you look at wind, it's very location specific. So we look at, okay, how do you interconnect it at that location? What's the strength of the system there and how can we move it? What size can we take? And then we do all the regulation studies as well and all the other integration studies. So yeah, we study things, but those are on a pretty specific timeline once you have a project identified. And that's what the RFP does. It helps us identify projects so that we can then do specifically targeted studies to try to bring that project along. It also depends on what the developer brings to the table. I mean, are they bringing, do they have enough data to allow us to study it? Do they have a good model for the type of inverter they're proposing? Do they have enough data for history of when the resource they're proposing? And, you know, so we work very closely with the developers to try to model things correctly. We don't do studies independent from the developers. Typically, they are, you know, funding some of this work, and they're very an integral part in trying to move things forward.
Well, I think that was the perfect ball to toss in regards to the next question. We do have a few more in the chat I want to get to, and we are running short on time, so we might go a few minutes longer than we initially planned here. What types of studies are required to be done by a generator owner before they can connect to the transmission system?
I've got the list up here, Ed, from our presentation that we did to the Alaska Forum for the Environment. Well, so I'll just run through them. First of all, you got concept development, economic modeling, interconnection study, impact study, regulation study. So I think, Ed, we were talking earlier, basically you're saying, how does it connect to the system and how does it integrate into the system? And they're two different things. So Ed, I'll toss that over to you to let you expand on that.
No, I think we talked a little bit about that already, you know, looking at the changes on voltage response to the system and all those level and how flows change on the systems and how that's going to affect our limitations on the system as far as that whole integration. So I don't think I need to go over that anymore.
All right.
If I can
Go
just
ahead.
Cap it off. What are you going to get? What concept do you have? What came from the RFP? Is it economic? In other words, do the big numbers, does it say it's going to pay off? How is it going to fit onto the system? And how is it going to act on the system? They're all different questions.
And how do we distribute it? And we haven't even gotten to those questions yet. So, and I'm actually going to pivot, and I want to close this out here with make sure we get to all the questions in the chat. And then I know there were some that we didn't get to in our list, so we'll close out by allowing each of you to kind of share some key takeaways that you would like to leave with the audience, with some insights or whatever that you would like to share with the audience here. So we've got 2 points here regarding Cook Inlet natural gas loss. One is asking what is the answer for energy source mixing to 2030? And the other was, again, I think Bill was kind of answering this question as he went in regards to the studies. Like, we know the natural gas shortage is coming, so how long do these studies take? And to add to the variability energy of the grid. So really kind of making up that difference that we know is coming. How are we approaching that? Who wants to take a first stab? Bill.
Sure, I'll jump.
Go ahead, Dustin. Go ahead, I was just picking on.
Well, regarding just a quick one on the how long do these studies take, it depends on the study. It depends on how in depth do you want to go, how far back are you going to look, how comprehensive are you going to be? Are you only looking at this one specific scenario? How many different interruption scenarios are you going to run? And so I guess, so in short, the answer is it depends. It doesn't take multiple years, but it does take a long time, and it takes, and oftentimes those studies produce results that say we need to do another study. And it's a very frustrating place to be, but I guess the best way to shorten that up is for a developer to bring as many the more studies you bring, and the better those studies are, meaning that they're studies produced by there's certain entities that do better studies than others, shall we say. And if your utility has faith in the person that did the study, that's going to have a lot more weight than a person that the utility is not familiar with. Also, just the more you bring to the table as far as knowing what your system is going to do, the more you've interacted with the utilities prior to getting there, the sooner it can be connected.
Ed, were you going to add something?
I'll just add, I mean, there are times when we have developers show up and they have a concept, right? They don't have financiers in place. They don't have the resource well identified. And as we move through our processes to do this studies, they're moving through their processes as well. We'll have an introductory meeting. They'll propose some range of pricing. We'll say, okay, if we can do that, that'll work for us, depending upon other costs associated with interconnection and regulation. We start looking at those prices. They get identified. At the same time, they're trying to put together financing. At the same time, they're trying to identify delivery time for materials. So again, these things are usually happening at the same time. I don't want to have it implied that the developer is typically sitting there waiting on us with something ready to go, because typically when we put out a request for proposal, we're getting proposals that have certain level of maturity to them. So it depends on really their level that they have in place. And some have relationships that are ongoing with financiers. Some have to go find them. And sometimes that can cost some time on their side as well. So we had a 6 megawatt project out at Houston. I mean, that was a 3-year project. From the time they knocked on the door till the time we had a project in place, all the financing in place, all, went through the regulatory approval process. So I think that was a small project where everybody wanted to make it happen. The community wanted to make it happen. MEA wanted to make it happen. The developer wanted to make it happen. And it still took 3 years from concept to putting it online. And that one, because it was distributed energy resource on the distribution system, and because its size was so small, took a lot less studying.
Dustin, you were going to expand on that? Oh, sorry, Ed, we're getting some feedback, if you don't mind muting. Sorry.
I wanted to throw in the extra complication that depending on where your project is, the interconnection, the transmission interconnection, could be quite difficult to achieve. So, for instance, we're looking at a wind farm that is not near the road system and not near, or at least relatively near, a transmission line, like the solar farm is up in the valley. So now you're looking at 14 miles of transmission, potentially through a state game refuge. I mean, this is going to take a long time to permit, not even to get the project done, just a permit to get the job done. So that adds a complicating factor that I really wanted to highlight for the group. But also, I wanted to address this the question about integrating the energy sources between thermal and renewable. I think one of the key elements that we're looking into is the idea that we have to essentially unconstrain the gas system. Right now, we have to specify a day ahead, 24 hours in advance, how much gas we're going to take by hour. And if we vary off that by very much, we get fined heavily under the existing contracts. So that's one of these constraints that says, okay, how are we going to move into this world where we can follow with fossil? We can, and when I say follow, I'm talking about regulating that variable power coming from wind or solar. How can we follow that with thermal resources when the input to the thermal is constrained, and we have to tell it a day in advance what's going to happen on a variable resource that doesn't care. So we're looking at various forms of gas storage in order to provide a buffer for that. So we can forecast a day in advance. We can go ahead and follow our gas dispatch. And whenever we don't exactly take what was specified, we can either put it in storage or take it out of storage in order to balance that out. So this is one of those elements that forms a transition between where we are now and where we need to be in the future with a high penetration of renewables.
Great. Thank you so much. And I'm sorry we're not going to be able to get to all the questions that we still have in the webinar chat. I do want to at least go around the table here and allow each presenter an opportunity to share some parting thoughts on where you think we're headed. What are some key considerations? What are some critical actions that need to take place? Just any key takeaways that you would like to leave with the audience from your perspective of a utility and transmission asset owner. Bill, you're at the top of my screen. I'm going to start with you.
The key takeaway, I think I'd kind of go back to the variable nature of the IBR resources and the challenge of integrating large penetration levels of those. It's oftentimes not as well understood by many of the people pushing it because they're looking at it from a lower 48 basis where there's that infinite grid, and up here it is not an infinite grid. And just to kind of go back to the scenario I was talking about earlier, if you've got 20% penetration in one of the regions in, let's say, Golden Valley, they lose the intertie, they may instantly go from 20% penetration to dramatically higher levels of penetration that they're not prepared for. And that the nature of our grid being 3 regions connected by an extension cord makes it incredibly difficult to increase the percent, to approach the levels of penetration that other places are doing where they have a much more robust transmission system. So I think that's probably the biggest takeaway I'd want to send. Hopefully that was clearly stated.
Thanks, Bill. Ed, how about from MEA standpoint? And you are muted.
I think MEA is excited about the challenge. We've reorged the company around, trying to accomplish this. We're excited that, we have a partner in Chugach Electric in this power pool that allows us to potentially, in this area of the state, bring on resources because we have more generation assets and differing generation assets to bring on place. So I think, we talk a lot about how to bring these resources on, and we can make it sound like it's something that we're not going to be able to accomplish, but history says we are going to be able to accomplish it. Transmission infrastructure, we're working on solving that problem too. We're working through DOE grants to try to expand transmission system, build redundancy on the transmission system, improve the stability of the grid in order to bring on regional assets that maybe can be brought on at a cheaper cost because we can get economies of scale and not have them isolated to a region. And the last thing I guess I want to bring apart is, we're talking a lot about transmission constraints, but there's also a lot to be said about putting these assets on distribution system circuits. I mean, they're smaller projects, so you don't get the benefit of economy of scale, but in general, they have less impact on the system, and they also don't require the significant cost to interconnect because you've got distribution lines that you can attach them to. So we've had some success that way. And plus, they provide other value to the system if they can eliminate the need to add capacity to a transmission line, a substation, a distribution line, because we can size generation someplace and reduce the load that has to be fed from a central generation plant. So I think there's a lot of positives as we move to a more clean energy future. And I just want to hopefully leave that as the main theme as we move forward.
Thank you so much, Ed. Dustin, last word from you, sir.
Just speaking for Chugach, I think the biggest leave behind that I want to provide to everybody is that the utilities are absolutely motivated to bring on renewable power, clean energy, in order to move away from this entire dependence on fossil fuels, especially natural gas. We understand that there is a payoff at the end of this, and we are working toward that future as far as trying to figure out how to deal with the variable power that's coming out of these systems. It's not a simple process, and you're dealing with an organization that deals with electricity. Electricity is not forgiving. It will not forgive you for even a momentary, I mean less than a second, excursion away from what's acceptable on the grid. That means that the distribution engineers, the transmission engineers, the culture of the people who work in the electric industry is very conservative, because we know it will not be tolerated in the rail belt to have the power go up just because we didn't have our act together. So we need to go through these studies, we need to identify these things, and we need to step into it responsibly. So that's the biggest leave behind I'll put out there, aside from saying there's the energy side that justifies the cost, but don't forget the power side where the engineers live. We're trying to get you to the other side of that river I was talking about.
Great. Thank you so much, gentlemen, for joining me today for this conversation and for the ability to share kind of some of the challenges that you're working through in this space from your perspective. So I appreciate your time and the conversation, and I look forward to having more of these as we move forward into the future. And with that, I want to close us out for today. Thank you so much for joining us. I hope you'll join us again tomorrow for the second half of our conversation. You'll actually learn a bit more about some of our transmission planning, the GRIP award that was referenced, and we'll also talk quite a bit about some MVDC interties. So we appreciate just in general all of our incredible presenters, the panelists, and of course, all of you, our virtual attendees. Special thanks to Government Event Services for doing a fantastic job organizing the logistics for this series. We hope everyone learned something today, and please encourage your friends and colleagues to join us again tomorrow, where we'll be diving into the MVDC and Railbelt hot topics. We look forward to seeing you all back here again tomorrow at 8:30 a.m. Alaska time. Have a great afternoon and evening.